The following message is best viewed on an oscilloscope.
So, hello, good morning, everyone. So this is the third session of Accelerator for ICHEP 220 for physics performance and R&D for future facilities. So today we have two blocks of talks. Totally, yeah, the first block will have 6 speakers and the second one 6 speakers, totally 3 hours. So each speaker has 20 minutes in total. In fact, 15 minutes presentation plus 5 minutes question and answer. So the first speaker, we will invite Yukioshi-san from KK.
Thank you, Hoji. So let's start. Highlights from Super KKB. I would like to talk on the luminosity performance by using nanobeam scheme and cloudwave scheme. These two schemes are novel techniques to realize extremely high luminosity. So this slide shows Super KKB collider. Michael Roney has already explained yesterday, but I would like to give you a brief explanation of this Super KKB collider. The circumference is about 3 kilometers, and the double ring asymmetric energy collider. The number of interaction points is 1 where the belt detector is located. And the target luminosity is 8 times 10 to 35 with these big currents as a final design. And the next slide shows final focus system. This final focus system is very complicated. The horizontal crossing angle is 83 milliradian to realize a nanobeam scheme and the separation of two colliding beams. And this is the history of the vertical beta function at the IP. We performed 1 millimeter beta Y star for the most of the recent operation. However, we could squeeze the beta Y star down to 800 micron at the end of the spring run this year. And the beta Y star at the Super KKB are 800 micron, which is the smallest value in the world. We move on the obviously micrometer world, but the final target is 300 micron. So we have to squeeze beta function by factor 3 from now. And if you are interested in the beam size, vertical beam size, the vertical beam size at the IP is now 0.22 micron, which is also the smallest value for the colliders. For instance, we can compare the beam size at SLC, which is about 0.7 micron. I found very interesting articles. SLC, the title is very cool, The End Game. SLC, The End Game, which is presented at the EPAC 2000 or 20 years ago. And the future collider, CPC and LCC, is about 1 millimeter or 2 millimeter beta west. Okay, so this slide shows the definition of the luminosity, specific luminosity, and the beam parameter used in the slides. In the case of the nanobeam scheme, such as a large beam scheme angle, the horizontal beam size can be replaced with a bunch length multiplied by the half crossing angle here. The hourglass requirement is modified by the real horizontal beam size divided by the half crossing angle. So consequently, we can squeeze a beta function the IP smaller than the bunch length. However, I would like to say the bunch length affects the luminosity as shown in the formula. So we should take care of the bunch lengthening due to the impedance effects. This slide shows the Crow-West scheme. We use a pair of sector poles here to move the west along the opposite beam line. We use 2 sector poles, which are connected by -I transformation. So we adapt opposite deviation from the reference field to make the Crow-West. If you see the interaction point, the inner particles in the horizontal direction have the defocusing, and the west move far from the original position. On the other hand, the outer particle have to have the focusing effect. Then the west move near from the original point. This is the Crow-West lattice in the area. HID is similar to area. 2 pairs of sector poles are shown in this in these figures. These sector poles are adjusted to make the Crow-West with keeping the chromaticity. This slide shows how the Crow-West sector pole works for the interaction point by using a simple tracking simulation. The left plot shows the phase space at the IP. This is the horizontal phase space, and this is the vertical phase space. If there is no Crow-West, the vertical phase space becomes a gray color. But when we adapt the Crow-West, the vertical phase space becomes red and blue color, which correspond to inner particles and outer particles respectively. The inner particle, red color, indicated by red color, should have positive alpha y and negative alpha y for the outer particles. So we can see the vertical alpha function at the IP, which indicates the west to move to the opposite beam line correctly. This is the operation history for 1.5 years in phase 3. Beam currents, HER beam currents and LER beam currents and luminosity. The total operation time is about 9 months. The vertical beta function at the IP has been squeezed from 3 millimeter down to 0.8 millimeter gradually since the last spring run. The peak luminosity was also improved as squeezing the beta function. This slide shows the recent operation summary for 4 months until this summer. The beam currents and luminosities shown in the figures. The maximum beam current is 770 milliamps in LER and 660 milliamps in the HER. The peak luminosity of 2.4 times 10 to the 34 was achieved, which is higher than the KKB record. The highest integrated luminosity per day was about 1.35 in the center band as a recorded luminosity. We also operated the off-resonance energy 2 times. We adopt Crow-West scheme for both area and HER, which is one of the new items. We adopt a high emittance lattice to reduce two-shake effects in area. the emittance changes from 2 nanometer to 4 nanometer here. On the other hand, we try to correct chromatic X-ray coupling by using rotatable sector port in the LER. Then finally, we squeezed beta function at the IP from 1 millimeter down to 0.8 millimeter. This slide table shows how much improved the luminosity, peak luminosity with Bell2 data taking. The peak luminosity is doubled for the operation by operation, even though the peak beam currents do not increase so much. Okay, this is the specific luminosity for 1 millimeter optics. The specific luminosity is much improved from 2019 autumn run shown in the figures. We can increase the higher bunch current product with cloud west and collimator tuning and linear improvement. However, we obviously observe beam blow up due to beam-beam interaction, because if there's no beam blow up, the specific luminosity should be constant. So we are trying to reduce beam blow up as much as possible to reduce nonlinear effects such as chromatic X-ray coupling and higher order effects. If we can add the specific luminosity for 0.8 millimeter beta Y star yellow plots, the specific luminosity increase as squeezing the beta vertical beta function at the IP if we compare the specific luminosity between 1 millimeter beta Y star and 0.8 millimeter beta Y star. In the case of 0.8 millimeter optics, we operate at about 0.3 milliamp square for physics run. So we can collision tuning with this region. But we also show the higher bunch current product larger than 0.4 milliamp square for 0.8 millimeter beta Y star. However, the collision tuning is not enough due to lack of operation time. So there's a room to improve the specific luminosity at the higher bunch current, more than 0.4 milliampere square for 0.8 millimeter beta Y star. This is the best shift, the beam currents and the luminosity. We always use the top-up injection to keep the beam currents. The recorded luminosity is about 550 inverse picobarn per 8 hours, and it is about 90% efficiency. This plot shows the bunch filling pattern. We introduce 2 abort gaps to make abort trigger fast as much as possible. The harmonic number is 5,120. However, we use less than 1,000 bunches stored, which are stored in this case. Of course, we can increase the number of bunches to increase total beam current. This table shows a comparison between the KKB and the super KKB, recent super KKB machine parameters and the final design parameters. The peak luminosity at the latest super KKB operation is larger than KKB record. Although the beam current, if you look at the beam current almost half of those of KKB. The latest super KKB machine parameters are still far from the final design. We have just started the challenge of luminosity frontier. Okay, so the summary, the peak luminosity of 2.4 times 10 to 34, which with a Bell2 data acquisition is a world record. The vertical beta at the IP, 0.8 millimeter is the smallest value in the world. Beam size at the IP also smallest. The super KKB applies a really large beam skin angle. The cloud-based scheme seems to work successfully, especially it's effective at higher branch current. The rotatable sector poles have been utilized to correct chromatic cell coupling in the area. The effort will be continued to the following operation. This may help to reduce beam blow-up. And collimators works well to reduce the detected background. We need a more precise adjustment. And however, difficulties arises significantly, such as extremely short beam lifetime, stability of operations. Sextupole and octupole tuning have to be performed to improve lifetime. If the dynamic aperture affected, the linear performance will be a key issue for the next autumn run to overcome one of the difficulties. Beam background and injector performance limit the beam current so far. The beam current comes from the stored and injector beam. I think 50% for area beam. The background 50% for area beam gas events. And the top counter uses PMT. So we have to consider lifetime of the PMT. And the target for the next autumn run is 4 times 10 to 34 by increasing beam currents. We consider to achieve 10 to 35 until the end of 2021. Thank you very much. That's it.
Oh, thank you very much. You have kept a good timing. Questions to you, Kiyoshi-san? So I have several questions if there is no from audience. In the last table, you showed the beam parameter evolution from the beginning and till now. So, but a little bit confusing. You use the word so-called the design parameter. For example, the final one, you put one line, this is the final one. I mean, this is the so-called designed. My question is, what is achieved compared to these so-called designed? Or you use this designed as the final achieved experimentally?
Of course, the target beam parameter 0.089 is a target, but still the branch current is almost smaller than half, or about half of the final design branch current. So beam parameter is about half, less than half.
Okay, so that is my question. So I never saw, I did not see the number of actual experimental obtained the beam number. So you said it's half of this one, right?
Yeah, but the HL beam parameter is slightly lower, around 0.02. So we want to 0.04.
Okay.
Yeah,
so
but in the area about very close to the 0.04 we achieved.
Okay, so anyway, this is halfway from the design goal.
Yeah.
Sure, this is the luminosity is not yet compared to your final goal. So there are many. So this is something. Another thing you said in your conclusion, but with words without number to say the very short lifetime. How about the actual lifetime now? The shortest
lifetime. Yeah, maybe I forgot to put the lifetime.
I mean,
maybe 20 minutes or so. 20 minutes and 30 minutes.
Yeah. I think this is reasonable. So in fact, this is really the difficulties because now you're 0.8 millimeter. If you squeeze down to smaller one, I mean 200 micron, of course, even 3 or anyway.
Yeah.
So this is very difficult. The lifetime will be dropped.
Design lifetime is about six minutes. 6 minutes, less than 10 minutes.
Okay. So
we need a much improvement of the Linux injector performance.
How about the lattice design dynamic aperture? If you reduce the beta Y, again, I'm afraid that you have a very small dynamic aperture, and then you have almost zero.
I think dynamic aperture is not so problem, because the physical aperture is very important for us, because in order to reduce the beam background against the detector, so the collimator, movable collimator aperture is very, very small in these operations.
Okay.
So the lifetime almost determined by the physical aperture so far.
Okay. Okay, so thank you very much, and congratulations. So the first day of your operation, I was in KK. So to see today, you will reach this high limit. I mean, this 800 milli beta Y. So,
yeah.
so this already a big achievement. I mean, for CPC, FCC, this reference.
Yeah, same level of the beta Y star of the CPC, FCC, I think.
Yeah, you are lower.
Those pilot somehow pilot machine for the future colliders.
Exactly. So this is
a crossing angle.
Also. So thank you very much.
Thank you very much.
So we have we kept 20 minutes exact time, and now we welcome Bernard to talk about the energy frontier this at CERN.
From Geneva. You see my slide?
Yes.
Okay, it's always the first question because we never really trust these modern techniques. I will present an overview about the studies that are ongoing at CERN and collaborators on possible future projects for deep inelastic scattering, mainly for LHEC, so electrons colliding with the LHC proton beam, and then also an option for the future circular collider, 100-kilometer proton machine in electron-proton collisions. I am talking on behalf clearly of a large team of colleagues that did these studies over the last years. It's a nice coincidence that today the update of the conceptual design report, CDR, is available as published on arXiv, and I got yesterday the link to this paper, which is available since now, basically. There's the front page on the lower right side, which is basically focusing on the Large Hadron Electron Collider and then possible FCCEH. Under the umbrella of these studies, we focus on three main possible scenarios. Has been presented just some days ago in a SNOMAS conference by Max Klein and Oliver. So this is the LHEC, the FCCEH, and very important, the Perle prototype machine. The LHEC is what I will focus today mainly, and you see here a sketch of the LHC collider, and then three different ovals in yellow or orange, showing qualitatively the geometry of the electron machine. So in the case of LHEC, we talk about 50 GeV versus 7 TeV protons. The operation, if we are optimistic, could start in 2035. And the CDR for this you have seen just on the first page. In an upgrade, we focus for 10 to the 34 luminosity for Higgs and beyond the standard model physics. Very closely related to this is the Perle project, powerful energy recovery linear for experiments, which is in the final design and starting construction phase in Orsay. Again, here you see the CDR, and this is very important for us because they use the same frequency for the RF system, 800 megahertz, 20 milliampere beam current, and an final energy of 500 MeV. So indeed, this is a machine that will prove the, feasibility of a high power energy recovery linear in Orsay, which will be then the leading project for the LHEC. And then on the right side, you see the FCC-EH. That means electrons on the level of 60 GeV colliding with 50 TeV protons. You see here the sketch of the FCC 100 kilometer proton machine in the Geneva Valley, and in black you see here the Geneva Lake. Here in this talk, I will mainly focus on the LHEC, but for the electron side, the energy recovery machine accelerator will be more or less the same for all three options. We are still discussing the size of the machine, so not the beam dynamics, but the circumference, which in the end, because of limitations in synchron radiation and the impact on emittance and beam quality, defines the reachable energy of the electrons. So we are studying a machine, for example, with a third of the LHC circumference, 9 kilometers roughly, which would get us to an electron energy of 60 GeV. Then there is an option, a fourth of LHC in the order of 50 GeV, and then a little bit smaller, a fifth of the LHC, shown as 3 circles here and a plot on the right bottom side. On the button on the left side, you see the first estimate calculations for the money that it would cost, the budget to foresee for the tunnel, the RF galleries and the shafts. It means the underground work in general. And it's clear, the higher the energy of the electrons will be, the larger the tunnel has to be, and the higher is the cost for the construction of the tunnel. So money goes together with the energy reach of the physics that we can expect. This is still under discussion, and there basically the high energy physics colleagues have to express their opinion. How much money are we willing to spend to get the highest possible energy? Luminosity, the parameters are predefined by the LHC, the Large Hadron Collider, in the high Lumi HL-LHC version. So the electrons basically in their beam dynamics properties have to follow the conditions of the proton beam from LHC as easy as this. We have a certain bunch pattern in LHC. We have a certain beam size defined by the mini beta focus lattice of the LHC. And then we have to match the electron beam optics in a way that we have nicely well-matched electron beam sizes in both planes at the IP. The luminosity then for such a machine is given by the number of electrons in a bunch times the number of protons, the number of bunches stored in the machine, collision frequency, and then divided by the beam size. There is a luminosity modification or reduction factor H, capital H here in the equation, which is the hourglass factor, the pinch effect, that means this additional focusing that we get, which is positive, and the fill factor, the fact that LHC needs some space for abort gap and injection gaps, etc. Taking all these factors together, we are pretty close to 1, so I will ignore them in the rest of this talk. So the luminosity is then defined by the properties of the LHC, proton number and collision frequency, and then the beam current that we can store in the electron machine, the ERL. Okay, a very short main parameter list. Here, I focus on an electron energy of 50 GeV colliding with the LHC protons, 7 TeV. Number of electrons per bunch is about 3 times 10 to the 9, corresponding to an overall current in the machine of 20 milliampere at the interaction region. The proton parameters are defined by the upgrade version of the LHC, 2 times 10 to the 11 protons per bunch, about 7 centimeter beta function at the collision point, and then the normalized emittance 2.5 micrometers, which gives us then for these electron-proton collisions a luminosity close to 10 to the 34, 9 times 10 to the 33 on paper. Here is a parameter list which is a little bit more detailed for your background information. I will not go through all these values here. This is just for bare information for those who are interested in more detailed numbers. Again, 50 GeV, 20 milliampere. The circumference here is the 1 divided by 5 of LHC, 5,300 meters. And then, as I said, the luminosity close to 10 to the 34. Remember, it is, considering the energy 50 GeV, a pretty compact machine. It is not a storage ring. It is an ERL, which allows us to be quite compact and so much cheaper. The circumference that I mentioned here, 5.3 kilometers, is even a bit smaller than the SPS, which is close to 7 kilometers, as I mentioned here on the bottom left part. Okay, I will go briefly through some models of this LHEC project. The Linux, the RF system, the frequency has been chosen 800 megahertz, 5-cell cavities, with a gradient a little bit lower than 20 megavolts per meter. This brings us then to the required overall energy of 50 GeV. We have two Linux in this oval geometry. So two Linux combined by the arcs on the left and right side of the machine. And the energy gain, the acceleration energy per pass, the bottom line it's mentioned there, gives us 8.1 GeV per Linux. Very nice opportunity to present you the result of the first prototype tests, the cavity quality factor here on the right side on the top, Q0, measured at 2 Kelvin. We are running at about 20 MeV, 20 megavolts per meter. The quench limit is much higher, in the order of 30, and the quality factor is pretty much constant between 10 and 20 MeV per meter. This is a very new result and a collaboration between CERN and JLab, which gives us really quite some optimism. Okay, all in all, each cryo module contains then 4 5-cell cavities. The challenge in the optimization of these cavities will be the large beam current. We have a 3-pass machine, 3 arcs. That means all in all, we add up these 20 milliamperes to 120 milliampere, a factor of 6 clearly. So these cavities have to be optimized for lowest higher order modes to guarantee the beam stability. All in all, we talk about 896 cavities running at the frequency of 802 megahertz, which is, I have been asked to tell you this just to give you a kind of scaling, less than 10% of the ILC cavity needs. So again, a pretty compact machine that shows the advantage of this ERL concept. The optics of the Linux is somehow straightforward. This is a 130-degree photo structure. Here on the right side, you see it with the cryo module schematically included. The point is it has to be matched for the beam optics of the 3 energy steps in each Linux. We have 2 Linux, so we have 6 energy steps for the acceleration and the deceleration mode, because after the interaction point, the beam will run in decelerating RF phase through the cavities, putting back the energy or the biggest part of the beam energy back into the RF system, which is what the ERL defines then. The arcs, here the highest priority and the challenge is the emittance preservation. We are far away from reaching the equilibrium emittance as we usually do in a damping ring or in a ring collider. So we take the emittance as defined by the particle source, and the only thing that we can do is to preserve it and handle it with care through the acceleration, then through the arcs, which is the main problem, the spreaders, where we distribute the beam into the, to the 3 return arcs, and then after the IP through the decelerating phase. We all know that the emittance increase is defined by this sans curly H function, H, which is then again defined by the dispersion and the optical functions as I show here. Therefore, it has been chosen for the low energy arcs, arc 1 to 3, and the high energy arcs 4 to 6, different beam optics. In the low energy case, the arcs are powered in an isochronous optics mode to keep the bunch lengthening punch elongation as small as possible. For the high energy arcs, however, we have to take care for the emittance, because the quantum effects of the synchronous light, they are very high. So here, basically, this is designed by Alex Bogash in JLab. Theoretical minimum emittance type lattice has been chosen, and I show you both optics here on the right side for a single cell. Okay, then after the arc, or after the LINAC, we have to run the beams through spreaders and recombiners to distribute them according to the energy into their appropriate arc. So the lowest energy beam after the first pass through the LINAC will be guided to the highest arc, and then for the highest energy we basically go straight forward in arc number, what is it, 5 and 6. These spreaders have been optimized since 2012. We go now for a non-dispersive, that means achromatic vertical deflection system, gently matched for the beam optics between the LINACs and the arcs. And I show you the latest result of the optics match on the right side on the bottom here. Here, a lot of care has been done, especially to preserve the vertical emittance, because this spreader spectrometer dipole, which is mentioned here in the schematic plot, creates clearly quite some synchronous radiation. It has to be strong enough to provide sufficient separation in the 3 arcs, which are one on top of the other. And on the other side, we have to avoid an emittance blow up here, which is intolerable. Synchronous light and emittances. And here for once, I mentioned 2 names. For the CDR, there are 337 authors, and you can have a look at them. But for the synchronous light, there are 2 people that provide a lot of calculations and simulations. This is Daniel Clayton and Daniel Henstock from Liverpool. They are internship students at CERN at the moment and working with me on this concept. So they established analytically and in simulations a complete synchronous light catalog for the machine for all arcs, spreaders, bypass, interaction region, etc. So just to show you, to point out the problem.
Excuse me, we used up 15 minutes of presentation, so be careful time.
Merci. We have to take care for the critical energy that is not too high. Here are the equations. So we have to optimize the whole machine in a way that we keep the critical energy low enough. And here is an example for a 4th LHC design size for the different arcs and energies. Okay, the interaction region then for the protons is basically the HLLHC proton optics, which is shown here. For the electrons, this is new, and here we have to combine the beam separation scheme, that means again a source of synchronous radiation and possible emittance dilution, with the mini beta concept. And we have a new design based on separation dipoles here on the left and off-center quadrupoles to keep critical energy and emittance effects as small as possible. One of these optimization scans that has been done is here on the right side to optimize the parameters of this separation scheme. The beam interaction has been studied. You see here on the left button the effective beam size without and including the beam effect, and a phase space diagram on the right side, which will be used then in XX prime, YY prime for the deceleration for the energy recovery mode, then to track down again to the injection energy. Okay, the next challenge is we are, I would say, pretty fine in the beam dynamics calculations. What will come then as next challenges and studies is the design for prototypes of the special machine elements, half quadrupoles in the interaction region, spectrometer dipole and the spreader, which has to be quite compact, 800 megahertz cavities for high current operation, which goes along with the parallel design, as I said. Synchronous light is always an issue in that kind of machine. And then the machine detector interface, how to protect the detector from the synchronous light that has been produced. Summary and conclusion. In 2012, a first CDR has been written. It is updated and published today. Nice coincidence. More than 300 authors. It considers and describes the physics, the accelerator, the parallel prototype machine, and then the detector. Here, I focused on the arc structure, synchronous light catalog, beam spreaders, emittance budget, and the interaction region optimized. Two final statements. The update CTR and the parallel project, they show the way to a TDR of the LHEC machine. I'm convinced that the energy recovery linear is really a key future accelerator technique. It's very efficient and goes a little bit in the direction of green accelerators. With the LHEC and the later possible FCC-EH, we get the highest resolution microscopes for deep inelastic scattering one may build with a striking potential on Higgs beyond the standard model top and nuclear physics. Here on the right side, the last plot, you see the improvement in coverage on the kinematic plane in deep inelastic scattering between, for example, HERA, LHEC, and FCC-EH. Thank you. That's it from my side.
Yeah, thank you, Bernard. And due to the time limitation, so we would collect one or two questions from audience. Questions? So if not, I would propose ask one question to Bernard. And about the beam, you showed the number of P and E. For the proton, which is in the order of minus 10 to minus 4, and to electron is about 1. So my question is for proton and electron, in fact, which one is the limiting?
Okay, this is, they are both limiting. We can show, and we optimize the parameters, that in case of the protons, we are far in the shadow of the high luminosity experiments ATLAS and CMS. So compared to what the protons see in the other IPs, the contribution from the LHEC is not very high. In the case of the electrons, I showed you this phase-space plot, and here indeed, we push due to the high bunch population of the protons and a very high energy proton beam, the beam parameter to a limit where we see then the onset of losses during the energy recovery process. Going down in energy after the IP means the emittance is increasing, and so this is a possible source of particle loss and inefficiency for the ERL process. So here, in case of the electron beam parameter, we have to be careful not to require too much.
Yeah, I think your answer is reasonable. Yeah, thank you very much. So yeah, so the next speaker is Phil. So Phil, you are here.
Yes, I'm here. Can you hear me okay, G?
Yes, voice is good, and so you can put in full screen and to move a little bit to the second page and go back to the first to see whether it works.
Does it work?
It works. So please start from beginning. Yes, thank you.
Okay, thank you very much indeed, Mr. Chairman, and good morning, everybody. So it's my pleasure to present the status and plans of the CLIC Accelerator project. I'm speaking on behalf of the CLIC collaborations. The last time that most of the collaboration gathered was last year. We've not been able to do that so far this year, but you see many of our collaborators here. So the outline of the presentation is shown here. So I'm going to give a very brief overview of the CLIC project. I'll talk about the technical maturity, the implementation of the CLIC design, our plans for the coming years, and then I'll give a brief summary at the end. So I think most people are probably quite familiar with the CLIC project, but in brief, it's a very timely project. So we are proposing an E+E- linear collider at CERN for the post-LHC era. It's based on a very novel, unique two-beam accelerating technique using high gradient room temperature RF cavities. And the first stage, the 380 GeV stage, would be 11 kilometers in length. And we have this staged approach to collision energy starting at 380 GeV for a Higgs and top factory, with the possibility to extend up to 3 TeV. The cost for the first stage is about 5.9 billion Swiss francs. So it's roughly comparable with the cost of the LHC in today's money. And the wall plug power for the first stage is about 168 megawatts, which again is well within the current power capability installed at CERN. The project is very well documented. We published the CDR in 2012, an updated baseline in 2016, and most recently the project implementation plan in 2018. And of course, there's a lot of work going on physics and detector studies, which have been presented in other talks at this conference. Just for reference, here are the documents that we prepared for input to the European strategy. So there are 4 yellow reports, a huge amount of documentation, an overview, physics and detector, physics overview, machine overview, and detector overview and R&D. And then these are the 2 documents that were submitted to the European strategy process. And you can find all of these, this documentation at this reference here. And of course, we are also engaging with the SNOMAS process in the United States, and we are preparing letters of interest for CLIC for SNOMAS. So this shows you the layout of the machine as it's envisaged in the region of CERN. So the first stage, the 380 GeV stage, is a little bit larger than the diameter of the LHC. And here you see the possibility to extend the LINAX to the full roughly 50-kilometer footprint of the 3 TeV machine just at the foot of the Jura Mountains. The concept of CLIC, again, I think it's probably reasonably familiar, and this is a diagram that shows you the layout at 3 TeV. You can see it's quite complex, but the idea is very simple. You have a drive beam accelerator, which has a rather low energy but high power drive beam, and you decelerate the drive beam in a series of decelerating sections, and you transfer the power to accelerate the main beam at roughly 12 gigahertz frequency using X-band structures. So it's a very novel concept, a 2-beam accelerator with a drive beam and a main beam accelerated to high energy. The layout at the first stage, 380 GeV, looks significantly simpler. There's a single drive beam which is able to feed both of the electron and positron LINACs, and there are 4 of these decelerating sections per beam, giving a total sight length, including the interaction region and so on, of roughly 11 kilometers. The parameters are shown here. I'm not going to go through these parameters in any detail, but just to remind you that for the first stage, the cost optimum accelerating gradient is about 72 megavolts per meter. And then for the higher energy stages, we're targeting 100 MeV per meter with the possibility to use the structures from the first stage. The luminosity target is 1.5 times 10 to the 34 at 380 GeV, rising to 610 to the 34 at 3 TeV. So these parameters are there for reference in case anybody has any questions. So this is how we would imagine staging the machine, and this shows the luminosity profile, starting off with the first stage. So there's an initial ramp up of luminosity as we learn how to run and commission the machine, and then steady state operation for roughly a total of 8 years. And so the plan would be to operate at 380 GeV with a dedicated run at the TT bar threshold, 350 GeV, to collect roughly 1 inverse attobarns of data, with then the option, as physics dictates, to go to the higher energy stages and to collect further data at higher energy. Now, of course, there are many challenges associated with the accelerator design itself. I can only give a very brief summary, but if you like, there are 4 principal challenges. There's to produce the high current drive beam and to bunch it at 12 gigahertz. There's to transfer power from the drive beam to the main beam. There's to achieve this 100 megavolts per meter gradient in the main beam cavities. And then there are many issues associated with the alignment and stability of the beams. So all of these challenges have been addressed at a number of test facilities. So CTF3, the click test facility, addressed all of the drive beam production issues. This X-band 12 gigahertz technology has been developed and verified through prototypes and through system tests and test stands at CERN and in China and Japan and many other places. There are two currently operating C-band X-ray free electron lasers, Sackler and Swissfel, and these provide huge facilities, large-scale facilities, demonstrations for normal conducting high-frequency, low-emittance Linux. And so we are learning a lot from these machines. And then many of the other critical issues, alignment, issues, for example, damping rings, beam delivery, and so on. These have been addressed at other facilities such as ATF and Facet. Now, power is, of course, a concern for all modern high-energy accelerators, and we've done a bottoms-up power estimate for CLIC. These are the numbers for the 380 GeV first stage, and you can see in the pie chart on the left how the power is distributed. The total wall plug power for the first stage is about 168 megawatts, which is certainly well within the installed site power capacity of CERN, and you can see how the power is distributed among the different areas of the machine. Now, many people are also interested in the idea of a klystron, an all klystron-based version of CLIC. So you would do away with the drive beam in this case and replace it with a system of modulators and klystrons. Interestingly, the wall plug power turns out to be more or less the same, 164 megawatts. And basically what you've done is you've traded off the power in the drive beam system here on the left, and you've replaced it with the power in the conventional modulator and klystron system shown on the right. So the power is very similar for both the baseline CLIC machine, the two-beam machine, and the klystron option. And of course, we're always looking at saving power. And so we are looking in particular at how, if we can be more efficient in the damping rings. We are looking at high efficiency klystrons, the use of permanent magnets, and we are reviewing the numbers for 1.5 and 3 TeV. Now, if you take the power budget and you fold that with the running model of the machine, you get the energy consumption. So this shows the assumed run model with number of days for different periods. So for example, data taking is about 140 days a year. And then you have the annual shutdown, you have stoppages for faults and so on. So this is how we imagine the calendar time would be distributed, and you fold that with the power and you arrive then at the energy consumed by the machine. And so what you can see here for the first stage, 380 GeV, is the actual energy consumption in terawatt hours. And the current CERN energy consumption is about 1.2 terawatt hours per year. So we're significantly below that for the first stage. But of course, we have to look more carefully at the higher energy stages to try to reduce this energy bill. And that we are doing. So we've done a very detailed bottoms-up costing of the accelerator, and the numbers are shown here for the first stage. The bottom line is that the first stage cost is roughly 5.9 billion Swiss francs in CERN core cost accounting, and you can see how that's distributed across the different areas of the machine shown here, and there's a table if you're interested in the details. Again, many people are interested in this possibility to replace the drive beam with klystrons, and we've looked at the cost of an all klystron first stage, and interestingly, it's significantly higher, and it's in fact dominated. This difference is dominated by the cost of the klystrons in the current cost of the klystrons for the RF system. So we believe that the baseline design, as we understand it presently with the two beam scheme, is certainly cheaper than an all klystron based option. Of course, there are other elements to the cost. So we've looked at the estimate for labor costs, which we estimate to be about 11,500 FTEs for the first stage. And then if you want to go to the higher energy stages, if physics dictates that we should go to 1.5 TeV or 3 TeV, of course, you need to lengthen the main Linux of the machine and upgrade other aspects of the complex. And so you would need to add roughly 5 billion to go to 1.5 TeV and roughly 7 billion, another 7 billion to go to 3 TeV. We've looked at the costs of operation, and it's roughly 116 million Swiss francs per year, plus the cost of electricity for the first stage. So all of this is a very detailed estimates of cost and power and so on, which has all been presented in the CDR and reviewed internationally. And so I think this summary take-home message for CLIC is that the key technologies have been demonstrated. It's a mature project, and we are ready to move towards implementation of this Higgs and top factory first stage at 380 GeV. The technical schedule is shown here. So from a decision to go ahead with the project, we think we would need roughly 7 years for construction, installation, and commissioning. And then we would initially plan to run for roughly 8 years at 380 GeV, including a top threshold scan. And then, of course, physics will dictate whether we need to have additional running at the higher energy stages. But this is the technical schedule as shown here. Now, I think you're all aware that recently the European strategy has been updated, and so I just pass a couple of comments on that. So I just show a few comments extracted from the strategy. So the vision is to prepare a Higgs factory. Well, we are certainly consistent with that, and indeed, more specifically, an E+ E- Higgs factory is the highest priority next collider, and the first stage of CLIC is exactly that. The strategy comments on innovative accelerator technology, not least high gradient accelerating structures, and we are addressing that in CLIC. And then there's a second document, the deliberation document, in which it's stated very clearly that the design, technology, and implementation aspects of CLIC indicate that the first stage, the Higgs factory, could be realized within 15 years and extended to higher energies. So we completely agree with that statement. And then again, there's a statement about the importance of normal conducting high gradient accelerating structures. So the CLIC R&D and design work is fully consistent with the European strategy and aligned with it. And indeed, this work will continue over the next 5 years in the medium-term planning presently under discussion at CERN. So let me just close with a couple of slides on some more recent studies. We've been looking at the performance at the Z pole, where it looks possible to get a higher luminosity than our default assumption. We've been looking at gamma-gamma collisions, and there's an example of a luminosity spectrum shown here. We're looking at the luminosity margins, and if you go from our baseline luminosity, 1.5 10 to the 34, the perfect machine after the damping ring, in fact, would have a luminosity roughly 3 times higher. And so there's a significant margin for improvement, and we're looking at our beam-based alignment techniques, our wake field steering, and other steering and tuning techniques to see if we can capitalize and increase the luminosity, taking advantage of this margin. We're looking at upgrades. In a sense, the conceptually easiest way to double the luminosity would be to double the frequency, and that actually looks reasonably promising. The cost increase is only about 5%, and it's a roughly 50 megawatt increase in wall plug power. So we are always looking to improve the performance of the machine, and these are some of the promising ideas under study. We are looking at the possibility of higher efficiency klystrons. This was mentioned by Ji Gao yesterday. And so now we are designing klystrons with a significantly higher efficiency in excess of 80%, which would be a benefit not only to CLIC, but to many other accelerators as well. We're looking at the industrial production of the CLIC accelerating structures, and an industrial survey shows the capacity is clearly available, and it would take roughly 5 years to ramp up to a stage of mass production. So then in closing, let me just point to the CLIC studies for the coming years. There's a lot of work going on X-band technology. You can read the details here, not only for CLIC, but structures for other applications. And so there are many applications of the X-band technology, including compact free electron lasers, medical linacs, inverse Compton scattering sources, and so on. And some of these projects are shown here. And so we are working very closely. We are plugged into many of these projects to spin off and apply the high gradient X-band technology. And then there are many technical and experimental studies going on, looking at the injector, optimizing the design of the CLIC modules, but also for other applications. Lots of work on beam dynamics. The CLEAR test facility, which is the new incarnation of CTF3, will continue to run, looking at wake fields and instrumentation and other issues. And we also work at ATF2 at KEK, looking at the production of nanobeams. And I mentioned already the high efficiency klystrons. So in summary then, CLIC is a mature project, and the 380 GeV initial stage is ready for implementation. We think the physics case is broad and profound, and of course it's being developed further. The cost and implementation time are similar to those for the LHC, There's a very well advanced detector concept and a lot of work going on detector R&D. All of the details you can find in this link here. And then in summary, let me just say that CLIC offers a staged and flexible approach towards the energy frontier. It keeps open other options, so it's certainly not in conflict with building circular colliders or indeed a muon collider. And it provides a path to very high energies in lepton collisions as the accelerating technology advances. So for the present CLIC baseline design, we think we can get to 3 TeV with the 100 megavolt per meter X-band structures. But of course, if you think very far ahead, you could reuse much of this infrastructure to get to perhaps very high energies based upon, for example, Wakefield acceleration techniques. So I'll stop there. Thank you to all of my collaborators for their support. And then I'm very happy to take any questions. Thank you very much.
So thank you very much, Phil. Very good presentation. So questions from audience? So Phil, about the high efficiency klystron, so what is the status now? It's already in the factory or?
Let me see if I can find this. So what's shown here, let me see if I can get rid of this. Yeah, so this is the present design, the latest design from Igor and colleagues. The chart is a bit complicated, but the this line shows the efficiency projection for this design, and the dashed line here shows the efficiency for an actual device which has been built and tested. So 70% has been achieved with the actual previous prototype. This is the upgraded one, and the projection is that we can even get beyond 80%. So this is now in development.
Okay, thank you. Other questions? So if not, let's thank Phil again.
Thank you very much.
Yeah, thank you. And the next speaker is Jenny on the polarized beam.
Yes, good morning. Good morning, everybody. Why are we at the last one? Don't understand this. And here. Yeah, it's a pleasure for me to talk about and discuss the role of polarized beams at future E+ E- colliders. And now it works. Okay, good. So for future E+ E- colliders, and in particular, of course, Higgs factories, longitudinally polarized beams are really a special feature of linear colliders. And both ILC and CLIC foresee 80% of polarization for the electron beam, and ILC actually also envisions a polarization for the positron beam. So this is, of course, interesting because any electroweak interaction is highly sensitive to the chirality of the fermions due to the L in our beloved SU2L cross U1 of the standard model. And thus every cross-section of every reaction depends on the beam polarizations. And so ILC with both beams polarized is, so to say, 4 colliders in one, depending on which configurations of the chiralities actually collide. So this has 4 effects. You can, with this, suppress backgrounds, you can enhance signals, you can actually analyze the chiral structure of the collisions. And I think what is least well known is actually that it's also important for redundancy and control of systematics, because if you choose the sort of wrong polarization with respect to your signal, you can get sort of a signal-free control sample. And especially this applies for the positron polarization if you want to use the electron polarization for the chiral analysis. So you have another degree of freedom there. Essential for this is the ability to quickly reverse the helicity for both beams. And so this means in the end of the day that this allows you to trade theory or detector systematics versus polarization systematics, which we think we can control very well, which will be the second half of the talk. So let's continue with why we actually want this. So obviously at every Higgs factory, the key process is Higgs Strahlung, production of a Z and a Higgs boson. And the standard model diagram, which you see on the left side, is this one here. But if you go to a general analysis in effective field theory, you could have other diagrams. Now, the point is, if you spin flip the chirality of the electron beam, then the first diagram flips its sign, the second diagram keeps its sign. So this means that the left-right asymmetry of these cross-sections really lifts the degeneracy between operators in effective field theory. And the result of this then goes into all these famous plots, which you have probably seen, of Higgs couplings precision for various couplings to various particles. And of course, the example I mentioned, of course, here mostly concerns the gauge bosons. And what is important to see here is that the green bars, which correspond to the typical ILC scenario with 2 inverse Attobarn polarized, are as high as the red bars, which are 5 inverse Attobarn, but without the polarization. And they are most of the time equally high, roundabout. So polarization buys you a factor 2.5 here in luminosity. And of course, higher energies improve this even further. So for the chiral analysis, the most famous example are, of course, the simple 2 fermion production, as you can see here in the diagram. And the vertex on the right-hand side actually hides 4 different couplings, depending on whether you have a photon or a Z exchange, and produce left-handed or right-handed fermions. And this is captured typically in a symmetry AF for the final state, and specifically for the electron. So at the initial state vertex, this relates directly to the electroweak mixing angle. So at an unpolarized collider, you can use the angular distributions, the forward-backward symmetry, but this gives you only the product of the initial state and final state helicity. While at the polarized collider, you can have an additional observable from the polarization, and this allows you to separately determine the couplings in the initial state and in the final state. So this is, and in addition, you can also trade here polarization against theory uncertainty, because actually the polarized asymmetry receives much smaller radiative corrections than the unpolarized version from the tree level equations given here on this slide. So a more concrete example of exactly this effect here for top pair production, you really see the disentanglement of the Z and photon exchange in the top production on this plot. So this shows the precisions achievable on various form factors, which is equivalent more or less to the couplings, the chiral couplings. And you see in red the Hailumi LHC projection, the most recent one, and then in blue the polarized case for the ILC, and in green the FCCE projections, which are unpolarized with roughly the same luminosity in this case. And you can clearly see the advantage of using the polarization and not only the final state analysis. The second example is from the same process. For any difermions, you can look out for 4 fermion operators, so 4-point interactions. And this is captured in an extension of the standard oblique parameters called Y and W. And here you can see in particular that the polarization is essential to beat down the correlations between the 2 parameters. Here, this is this column labeled rho. So this goes down by more than a factor 2 with polarization. And actually, in the polarized version already, the first stage of the ILC here really outperforms LHC significantly. This was sort of electrophysics at high energies. You can, of course, also do this at lower energies, at the Z pole. And typically here, the moderate giga-Z assumption already gives you a factor 10, sometimes even 50 improvement over the current knowledge from lab and SLC. I'd like to highlight in particular the charm asymmetry, which gets nearly a factor 100 better thanks to excellent charm tagging, based on, of course, the advances in vertex detectors, but also due to the tiny ILC beam spot and the kaon ID, which is possible via the specific energy loss in ILD's time projection chamber. If you compare the red ILC to the gray FCC TerraZ bars, you see that, of course, a factor 1,000 of more luminosity gives you better results, but actually it's only a factor 2 to 3 better, which means that polarization here buys you a factor of 100 roundabout in luminosity. Final example from BSM. So for dark matter searches in the monophoton channel, polarization tunes down the standard model backgrounds by a factor of 10, as you can see here in the plot. But at least as important is the fact that all these distributions also depend on the sign of the polarization combination, which helps you to beat down systematics if you then combine them. And this you can see here in this example, where you can see the new physics scale probe. So in this case, higher bars are better, different running scenarios sorted by energy. And if you look, for instance, here, you can see that the unpolarized versions really don't reach any further, even if they have much higher luminosity. Yeah, so like here in this example, 10 inverse Autobahn unpolarized is not any better than only 200 inverse femtobahn polarized. On the other hand, of course, energy helps as another feature of linear colliders. Once you increase the energy for any search, this is, of course, very helpful. So how do we do this? I mean, the source design is known since a long time and published in the TDR. I would like to highlight here in particular the spin rotation section before the damping ring for the positron side, which has been redesigned post TDR to implement this fast helicity reversal, which I've been mentioning. And as you can see here, this is done with two different beam lines with a kicker which switches between them, which obviously tells you that this reversal can never be perfect. So the absolute values will differ somewhat, and we will see later that we can handle this easily. So for the polarization measurement, we can exploit these benefits, physics benefits, only if we know the polarization really at a per mil level. And we achieve this by combining three things, namely Compton polarimeters, which are located upstream and downstream of the interaction point. We use spin tracking simulations to relate these measurements, and then combine this with collision data from the main interaction point. And there, of course, the crucial question is, which I will show you, is that we can disentangle this from new physics effects. So Compton polarimeters provide a fast measurement. You get order of 1,000 scatterings per bunch, and the energy spectrum of the scattered electrons depends on the product of a beam and laser polarization, and you measure the symmetry with respect to the laser helicity. Do this by using a magnetic chicane to translate the energy distribution into a position distribution. The uncertainty which we think we can reach is about 0.25% on the polarization at the polarimeter location. And you see in the table a breakdown of the budget compared to SLC. So this is typically a moderate improvement, which has been studied in detail, and I don't have time to explain this, but we think this is well under control. we have two polarimeters per beam, which have very complementary properties. So the upstream polarimeter has a very clean environment, benign beam condition, and samples really every bunch and is very fast. On the other hand, the downstream polarimeter gives you access to the depolarization and collision and has to face, on the other hand, a bit tougher beam conditions. So the combination of these two really without collisions gives you direct access to really understand the spin transport and the beam delivery system and the extraction line, while with the collisions you really can measure the depolarization at the IP. So for the spin tracking, a tool has been developed called STORC, Spin Transport at Linear Colliders. This is based on BMAT with interfaces to the polarimeter simulations and to guinea pig for beam-beam simulations. And an example result is, for instance, the cross-calibration of the polarimeters without collisions, where you can see here from the breakdown in the table which effects have all been studied, and that you get less than a per mil uncertainty from all of the studied effects. Coming finally to the polarization from the collision data. So a classic approach which has been studied for a long time is to use one polarization dependent process, for instance, W pair production, and determine then the polarization and possibly other important parameters like charge crippled gauge couplings, which are BSM sensitive. This works because typically central scattering gives you sensitivity to new physics, while scattering in the very forward region is determined by the polarization. More recently, we extended these studies to global fits to many differential cross sections of basically all 2 fermion and 4 fermion processes, and determine then the polarization values, cross-section asymmetries, and charge triple gauge coupling simultaneously. All this does not rely on perfect helicity reversal, but determines 4 independent polarization values. And this you can nicely see here on the left-hand plot for the 2 electron polarization values, where you can nicely distinguish the perfect helicity reversal at 80% from sort of any other offset from the exact flip. And in all this, still the polarimeter constraint is polarimeter measurement contributes significantly, as you can see here on the upper plot by comparing the full lines with the dashed ones, which include the polarimeter constraint. I showed you this for the electron polarization, but actually you can reach this per mil level for all the 4 polarizations, as you can see here from the blue crosses. And this shows you actually a bit the complexity of this whole analysis, because this is the graphical display of the correlation matrix of all the fit parameters. And the only thing I want to highlight here is that this box in the upper red corner is actually more or less empty, showing 0 correlations between the polarization and actually the luminosity and parameters which are sensitive to new physics, namely triple gauge couplings and here some symmetries. So which tells you that there is sort of no conflict between possible BSM contributions and a precise determination of the polarization. This brings me to my conclusions. So I hope I showed you that beam polarization is an integral part of the linear collider physics case, or in Higgs, in electroweak at high energies, and at the Z-pole and for BSM. This requires the knowledge of the polarization at the per mil level, and we have a concept for reaching this, which combines polarimeter spin tracking and global analysis of collision data. So. So we have this under control and can fully profit from its advantages. And I close with a list of talks I referenced, and tomorrow afternoon we offer actually a Zoom session to discuss further questions on all these ILC related talks. Thank you.
So thank you very much, Jenny. So questions? Any questions to Jenny on polarization?
I raised my hand. Hi.
Oh, sorry, please.
Yeah.
I did not.
Hi. Yeah. So this is actually also a question to Phil. As far as I recall, all these ILC and also CLIC, they are really, let's say, nanometer beams where the collisions, it's, let's say, each collision is like a new collider. So what I'm now like to ask is how you fold in time stability. Yeah, the stability over time. This is either for the polarization, which acts then like the luminosity stability over time, or then if you have unpolarized beam, then it's for the luminosity itself. Yeah, how is this controlled to this high level of precision if one considers that one has these nanometer beams that collide again and again?
Yeah, I mean, this is of course considered, Uta. I think Phil is the expert to answer for the luminosity stabilization. For the polarimeters, I can tell you this is exactly one of the reasons why we have, for instance, why the polarimeters are so important in the measurement, because particularly upstream polarimeter can basically measure polarization for any two subsequent bunches if you want. Yeah, so then of course with a bit larger statistical uncertainty, but still in principle you can completely time profile even what happens during one bunch train, and you for sure can control this on a train by train basis, but even the development during the train can be measured. Yeah, and it would of course be naive to just say we don't need polarimeters and just take this from the long-term average from collision data, right? So this is exactly why we need why we think we need this combination. Yeah? And of course
is it then really at this level of precision? Because I'm doing this atlas also, this exactly, and we have, and there the dominant systematic uncertainties are really then anything which is related to calibration transfers. Let's say, even as you also pointed out, that of course you can measure in the non-colliding beams, yeah, like the absolute calibration, and then of course in collision the polarization is different in collision, as you pointed out. And this is then again, if there is the transfer, and if this is then everything controlled really below the per mil level, it's let's say, it's still a little bit hard to believe.
Well, I mean, the ultimate test will of course be to build the machine. All I can tell you is that we simulate a lot of time-dependent effects, also like ground motion, like other misalignments which might change, and an important as far as one can simulate all these effects, they are considered and seem to be under control. I think one important thing in all this is, for instance, exactly also this fast helicity reversal, because we could absolutely not achieve this level of precision if we would flip the spin like it was done at Hera by going into the tunnel and moving magnets around and doing this, every 2 to 3 months. Yeah, then of course you would be lost due to the time-dependent effects you mentioned. Yeah, so I think this ability to train by train really reverse the polarization is really important here also for controlling these time-dependent effects.
Okay, so maybe this subject we can continue tomorrow, as Jenny indicates. So there is another discussion time. So thank you very much, Jenny. So let's welcome the speaker, Angela.
Hi, good morning, everyone.
So would you please share? Okay.
Yes, I guess that you are seeing my slides.
Yes, go ahead.
Yeah, so then before starting, I would like to thank the organizer for giving us the possibility to report about the most recent results we got after having changed the main muon target production in the context of the high intensity muon project beam at PSI. So let me just to then remind you, let's say, what we are talking about. Let's say PSI is actually delivering the highest intensity muon beam in the world at low energy, with an intensity up to this 5 times 10 to 8 muons per second, and aim would be to actually match the 10 muons per second in a time schedule that will be basically in the next year. And this is in order to address, first of all, a lot of experiment from the particle physics side, like future charge lepton flavor violation experiment, but not only, also a muonium-based experiment, and also open the possibility for new opportunity from the material science of all experiment based on the MUSR technique. Now, let me remind you that actually on the world already, we know that there are other places where people are pushing for increased muon beam, like Fermilab and JPark, but it's also true that in this case, while we are talking about, let's say, pulsed beam, in our case, we will stay and remain focused on continuous low energy muon beam. And this is basically because actually different experiment demand for a different beam characteristics. So basically pulsed versus continuous, and also, let's say, another important parameter is the energy of the beam itself. So in this respect, actually, PSI is pushing for a keeping and maintain the leadership in this low energy continuous muon beam. And here just an example of the difference in terms of, for example, high beam intensity, in terms of the time characteristics, pulsed versus continuous. And now if we are going to refer to charge lepton flavor violation experiment, if we are interested, for example, on pushing on the research based on the MUE conversion, for sure, a pulsed beam would be the best choice. While if we are interested more on a MUE gamma decay, MUE2 decay, where then more than one particle is in the final state, for sure, let's say continuous muon beam would be the best. And reason is associated to the control of the background. So now back to PSI. This is actually the PSI landscape, and his Earth, which is represented by the proton ring cyclotron with a power equivalent to 1.4 megawatt. So this is what you would see if you will visit us. Everything starts with the Heckel-Walton accelerator. Here is the path of the protons beam going through the ring cyclotron. And here we have the two muon target production, the so-called target M here and the so-called target E here. And then finally the beam is dumped in what we call the neutron spallation source. So then basically, let's say in our case, let's say the machine works in order to produce, let's say, this surface muon beam, which are polarized, as we can quickly reconnect to the fact that they come from the pion decay. And actually, let's say in this case, the surface muon beam are associated only, let's say, to the positive muon beam. And in terms of actually, let's say, the HIM project itself, so then our first starting point was to start with an optimized Monte Carlo simulation tool. And this was basically implementing some new two available parameterization that are based on measured data that have been obtained both at Los Alamos and PSIs, in order to bypass actually the fact that Gen4 didn't have, let's say, the pion production cross-section optimized for low energy. So the first step was for us was actually to first validate the code, and this was done running Monte Carlo simulation and comparing it associated to, let's say, one or several beam lines that we have at PSI. This is just one when we could actually got a very good agreement between Monte Carlo simulation and what we could measure. So basically at that point we were ready to say that we could start to use, let's say, our Gen4 updated code in order to exploit the possibility of this HIMP concept. And the initial idea was actually to try to get benefit from the neutron spallation source. In fact, let's say what happens is that a large fraction of the beam goes through the two targets that I mentioned at the beginning, and then it's really stopped at the end. Let's say 1 megawatt of the 1.4 in total is in fact dumped on the CQ. And actually Monte Carlo simulation told us that yes, we were right. We could have, let's say, up to 10 to 11 surface muon beam, but in fact, in order to then extract the muons, here is just a picture of the structure of the spallation source. Here is the proton that coming in order to extract then the muons which are produced at the SynQ spallation, in order to be efficient on this extraction and then the transmission, it was actually important to do important changes here at level of, let's say, the SynQ structure itself. And what actually turned out is that due to the existing constraint associated with the SynQ, we could not get enough captured muons for actually delivering a high intensity muon beam. So basically this forced us to do a step back and try to ask if there was basically room for improvement at the level of the standard muon production target, and also at level of the beamline itself. Here, just to tell you how the current target E, which is the main muon production target we have at PSI, looks like. Here, let's say this green arrow show you, let's say, how the protons are impinging on the target, and here you can see, let's say, the secondary particle, and here all the characteristics of the target itself, which is rotating, and actually that should also, let's say, dissipate quite a lot, let's say, energy deposit, which is equivalent to this 50 kilowatt. Okay, so then the point was to see if there was room for optimization at level of target, for example, thinking about different material and also different geometry at the level of the beam line, for example, trying to push for having higher capture efficiency, for having a better transport of the muons through the beam line itself. And now, if you go back and remember that we are talking about a surface muon beam, let's say basically the muons which are produced from the decay of the pions along the skin of the target itself, we can immediately realize that if we want to increase the muon yield, we should expect to increase, let's say, the stop density of the pion itself. Of course, the geometry of the target has also an impact, because you want to have an extension of the target, which is as much as possible in order to collect from the beamline side, let's say, the muons, but you should also allow the muons to go to the target itself, because we are, let's say, interested in having this low energy muon beam, which means, let's say, that the momentum is 28 MeV over C. And just to give you a reference, the range of such a muons is equivalent of 1 millimeter if we are talking about, for example, plastics. So then if we are going to do our exercise, what we are going to discover is that while, let's say, the pion yield increases as a function of Z, as soon as we should also consider the possibility of having the muons out from the target, what happens in practice is that the relative muon yield is going to follow, let's say, the red point that you can see on the plot. And that means that actually, let's say, the best choice for the target still remains low Z material, which means basically a graphite. Even if, let's say, we can consider the possibility of increasing a bit, for example, changing from graphite to a boron carbide. So the next step was actually to try to think if then, let's say, we could, let's say, improve it in terms of geometry itself. So the first simple exercise was just to have our target with the proton impinging on it and then increasing the length of the target, and then prove that if we are going now to collect the muon from the side of the target itself, let's say the amount of muon yield is basically scaling linearly, let's say, with the length itself. Of course, this is the easy thing, and what I mentioned at the beginning, this is a solution that we cannot apply straightforward, because we have the constraint that we should preserve the beam characteristics after that the beam is impinging on our muon surface target. We should preserve the beam characteristics for serving the neutron community for each reaching, let's say, the neutron spallation source. So then the idea actually was try to think about, let's say, a solution that could keep the amount of material seen by the proton as was originally, but try to then increase the amount of surface that can be seen by the beam line when we are going to collect the muon itself. And we consider actually several several geometry and turned out actually that the selected target would be the optimal choice for us, giving the possibility to increase it by 1 point factor, which is this 1.5 highlighted here. Now, as you can imagine, of course, let's say the amount of muon yield is a function of the target rotation angle. So this is how actually, let's say, the amount of muons is changing as a function of the target rotation angle, seeing the beam from the sideway, backwards, and forward. And our choice was actually to keep, let's say, the target rotation angle as at a small value in order to have the three different, let's say, configuration similar in terms of relative yield. And then the next step was then actually, let's say, to build a new target with the goal of prove that we could increase the surface muon rate for all connected beam lines that look at the target with different angles, and also increase the safety margin for missing target from the proton beam. And this you can figure out it immediately if you're going to compare, for example, the geometry of the new target, which is listed here, with the geometry of the old target, which is basically shown here. So what we did was then, let's say, change the target E. This is the position of the target E along of the muon beam, or along of the proton beam line at PSI. And here are basically the four experimental areas that are looking, let's say, at this target. And this was the expected enhancement in terms of muon yield. And what actually, let's say, we can tell you is that the increased muon yield have been confirmed, even if, let's say, the analysis is still ongoing. This is a solid statement. And actually, let's say, the current target that we have at PSI is, let's say, this new target. And what we have to now confirm is the impact of higher thermal stress on, let's say, long-term stability. So in terms of the experimental activities, let's say the measurement of the beam rate have been done every time simultaneously by two independent detectors. Here, a detector based on a scintillating fiber coupled to silicon photomultiplier, and here, let's say, what we call, let's say, pre-detector scintillator coupled, let's say, to a photomultiplier, and the two, let's say, detector actually gave us, let's say, rate and beam profile characteristics that were consistent at the level of the percentage. Then, let's say, the next step will be really now to move towards the high intensity neon beam project. After that, at least we got the confirmation of the increasing of the rate based on the target optimization only. And then the idea would be in this sense to actually to move from the position of the target E to the current position of the target M, and to promote these two beam lines here in the new, let's say, new high intensity neon beam line, able to deliver up this to 10 muons per second. Here actually how, let's say, the sketch of the new target look like. Let's say here is the original, let's say, make target, and this would be, let's say, the new one, the upgraded one, and also here how, let's say, the two beam line would look like. Let's say we have the two, let's say, normal conducting radiation hard solenoid close to the target to capture the surface muons, and basically here you can see how the general beam line should look like. We are starting, let's say, from here, and then we go through, and then in order to deliver into the experimental area this 10 muons per second. Now the final beam optics is still under development. Nonetheless, I can show you, let's say, how, let's say, the new beam line, this pure solenoid beam line, looks like compared with the standard and the best beam line we actually have at PSI, which is a hybrid beam line, the new E4, let's say, beam line. And now you see that actually starting basically from the same amount of surface muons available at the target level with an improved capture here. We are changing from 6% to 26%. And then they improved the transmission from these 7% here to the 40% here. We can actually end up with this 10 muons per second. Here, actually, there is a list of the things that still we have to do, let's say, from the beam line itself. But nonetheless, let's say, based on the nice results that we got from the target side, we are quite confident that we would be able, let's say, to address all these points in the next sphere. So this basically brings me, let's say, to the conclusion of the talk. Let's say, and again, here I would like just to remind you that the aim of the HIMP project is to deliver this up to 10 to 10 muons per second. Then the initial simulation showed that such rates are feasible. Actually, let's say the idea of this HIMP project is based on the optimization of the target itself and the beamline. And from the target side, let's say the new target have been successfully tested and the increase of the muon rate have been confirmed and to be consistent with what was expected. Now, from the beamline point of view, let's say the beam optics are under development, and probably the most important message we would like to share with you is that actually put into perspective the target optimization only, which correspond to this 50% increasing of muons. This would correspond to effectively raising the proton beam power at PSI by this roughly 600 kilowatt. That would mean basically to change from 1.4 megawatt to 2 megawatt without the additional complications such as, let's say, increased energy radiation deposit into the target and its surrounding. And actually, if this would be confirmed also that from we could get this 10 to 10 muons per second, and then if we repeat the same exercise, putting into perspective the beamline optimization, this would be equivalent to a beam power of the order of several tens of megawatt. And then based on that, let's say we are convinced that HIMP would open the door to actually interesting physics opportunity for particle physics, a charge lepton flavor violation experiment, and not only also experiment based on muons and also neonium and material science. And basically this is all, and we would like to leave you with the final remark associated to the input that was submitted and recognized by the European Strategy Committee, associated in particular here to the focus on the charge lepton flavor violation searches. Thank you very much.
So thank you very much, Angela. And questions? So I did not see any raised hand. Any question from audience to Angela? Okay, so if not, so I would say the recently the muon collaboration is underway to establish. So we received also the invitation to join. I mean, from Daniel Schütte. So the muon, so any technology connected with muon beams and experiment and technologies, I think is extremely important. So we are very pleased to hear the PSI reports on these subjects. So thank you very much, Angela.
Thank you very much.
Yeah, so the next speaker from Jay Park from Tetsuro.
Hello, can you hear me?
Yes, we can.
Oh, okay, so just a moment. So I'm sharing my slide.
Okay. Yeah, we can see full screen.
Oh, do you see full screen mode?
We see, but it's a two page, a little bit small.
Oh, sorry. Ah, just a moment. So.
So in your side, maybe only one page.
Sorry, how about this?
Perfect.
Oh,
so
okay.
Let's go back to first page and yeah, go ahead.
Okay, so first of all, so thank you very much for giving me this opportunity. So I'm Tetsuro Sekiguchi from KK J-Park. So I'd like to report on the J-Park neutron beam upgrades towards 1.3 megawatt beam power for long baseline neutron oscillation experiments in Japan. So I'm reporting for JPARC neutron beamline group. So this is the outline of my talks. So first, I briefly overview of accelerator neutron beam. And then, so main topic is JPARC neutron beamline. So current status and future upgrades. And finally, so I would briefly report on the international cooperation high power neutron beam, and then summarize this talk. So overview. So accelerator-based neutron oscillation experiments are playing an important role in Newton physics since 1999. So recent T2K, so T2K is the Tokai to Kamioka long baseline neutron experiments. So show the hint of large CP violation in neutron sector. So we are producing a neutron high intensity neutron beam at JPARC and sent the beam to Kamioka direction, middle of Japan. And so next generation experiments like Hyper-K and DUNE are aiming to reveal a full picture of neutron oscillation with precise measurement of CP and mixing parameters, and also determinations mass ordering. So those are unknown in Newton physics. So currently, sensitivity for CP variation is 2 to 3 sigma level, but in future experiments, so we aim to achieve more than 5 sigma for discovery. So we need more than 10 times larger statistics than current experiments. So number of neutrino proportional to the neutron flux times neutron cross section times number of target nuclei in detector. So neutron flux is proportional to beam power. Also, number of target nuclei is proportional to the detector volume. So to achieve larger statistics, so we need nearly 10 times larger new detectors, and also more than 1 megawatt class beam power needed. So I briefly show you the progress on the high power neutron beam. So the first long neutron beam for the long baseline neutron physics is from neutron beam from KEK 12 GBps proton synchrotron for K2K experiments. So starting 1999. So the beam power was 6 kilowatt. So this is the first generation of the long baseline neutron beam. So then, from 2005, so NUMI beam and also SUN CNGS beam started, and also from 2010, so JPARC neutron beam was also started. So and also NUMI upgrade with 700 kilowatt. So these are so-called second generation order of 100 kilowatt beam. So next step is beam power improvement towards more than 1 megawatt. So this is third generation of the neutron beam. Okay, so I briefly explain how to produce neutron beam. So we accelerate the proton beam. So in JPARC case, 30 GeV proton beam hits the graphite target. So and then secondary pions are kaons are focused by magnetic horns and decay into neutrinos as muons. So in the decay volume. So positively charged pion can decay to muon neutrino, while negatively charged pion can decay to anti-muon neutron beam. So we can select sign of neutron beam by flipping the home polarity. So then, all the hadrons are absorbed by beam dump, and just behind the beam dump, so high energy muons are monitored by muon monitors. So this is bird's eye view of JPark. So JPark consists of the 3 accelerators. So one is 400 MeV LINAC and 3 GB rapid cycling synchrotron RCS and 30 GB main ring synchrotron. So, and we also have 3 experimental facilities. So one from RCS. So we have we use 3 GB proton beam for the material and life science. And from 30 GB main ring, so we use proton beam for the neutron experimental facility. And also there is another, so hadron experimental facility. So this is a schematic view of the neutron beam line. So accelerated 30 GB proton beam is extracted inward to the neutron beam line. So primary proton beam line consists of the first straight section and final straight section, and also arc section. So equipped with superconducting magnets. And here is a target station. So which includes a target and magnetic horns, and 100 meter long decay volume, and also beam dump. And there is a neutron near detector located at 280 meter away from the target, so to monitor the neutron beam. So this is the status of JPark neutron beam. So we started physics data taking in January 2010. So then, this horizontal axis shows the time, and the vertical axis shows the accumulated number of protons on the target. So blue line shows accumulated POT. So dots shows achieved beam power. So, and the pink band shows beam time. So for each year. So, and we so far, so we achieved 550, 15 kilowatts stable operation with 2.66 times 10 to the 14th protons per pulse. So this is the world highest intensity in fast extracted beam from proton synchrotron. So, but beam power is limited by space charge effect and also beam instability due to insufficient output voltage, so which needs improvements. So for T2K data taking, so this main link provided 3.64 times 10 to the 21st protons on target so far. So almost 55% neutron beam, and also 45% anti-neutron beam. So this is status. Okay, so let's move to the JPark upgrade toward 1.3 megawatt. So we have a staged accelerator upgrade toward 1.3 megawatts. So there are 2 ways to increase beam power. So one thing is to achieve a shorter cycle. So current cycle is 2.48 seconds. So which is will be reduced to the 1.32 seconds to achieve design power of 750 kilowatt. So this will be done in 2021. So, and also another thing is increasing beam intensity, so to achieve higher beam power. So, and this bottom table shows current and upgrades, so beam power, intensity, and cycle. So currently 0.5 megawatt. So with this number, so and so for the upgraded scenario, so we increase the proton intensity to 3.2 times 10 to the 14th protons per pulse, and finally reducing to the 1.16 second cycle. So this bottom right plot shows expected beam power as a function of time. So first upgrade will be done in 2021. So by replacing main magnet power supply. And then, so after that, so we gradually increase the beam power. So by upgrading the RF system. So final goal is 1.3 megawatt. So to be achieved around 2028. So this is a scenario for the accelerator upgrade. And for the Newton beam line, so we also need so significant upgrade. So I will explain from now on. So so basic design of the JPAC Newton beam line is so design beam power is 750 kilowatts with 3.3 times 10 to the 14th proton per pulse. So and for replaceable components like horns and target, so designed for 750 kilowatt, but non-replaceable component like so the helium vessel, decay volume, and the beam dump, so were designed for the 3 to 4 megawatts. So necessity upgrade towards 1.3 megawatt is so yeah, improving cooling capacity to remove the higher heat generated by higher power beam. So this includes target rim cooling and water cooling for horn, helium vessel, and so on. And so another upgrade is to accommodate the shorter cycle operation, which includes a horn operation, the DAQ. And from the high power beam, so large amount of radioactivity will be produced. So we upgrade the radioactive waste disposal facility, so especially for the radioactive water. And for the high power beam, so safe and reliable control is necessary. So we are improving the control system and beam monitors. So one example is the target upgrade. So original target design is to survive a thermal shock by 3.3 times 10 to the 14th protons per pulse. So this value, so 3.2 times 10 to the 14 should be okay. So but cooling capacity is only 900 kilowatts. So we need improvement. So to achieve, so we will achieve the higher helium flow rate, so to improve cooling performance. So, and in this case, so higher pressure helium gas flow is needed. So from currently 1.6 bar to 5 bar, so to achieve a double flow rate. So, and so helium compressor system should be upgraded. So we performed a thermal simulation for 1.3 megawatt case. So, and expected temperature of the target core is 900 degrees C. So we will further optimize this design. And for helium circulation line, so vacuum insulation pipes now developed for the higher temperature helium flow. And also prototyping the new target with the high pressure tolerance is ongoing. So, and helium circulation system and will be upgraded. So in fiscal year 2025. So for horn, horn electrical system will be upgraded. So for 320 kiloamps operation at 1 Hertz. So original design of the horn current is 320 kiloamps, but we are now operating at 250 kiloamps due to some power supply problems. So, and so by achieving a higher current, so we can gain the 10% Newton flux, and also we can reduce 5 to 10% flux reduction for the long sine Newton background. So we developed a new power supply, a new transformer. So this is the current configuration. So for 3 horns, so we have now 2 power supply systems. So 1 power supply for 1 horn and 1 power supply for so 2 horns in series. So we will increase the number of power supplies. So and so first, so we will achieve a 1 Hertz operation. So after 2022, and later, so 320 kiloamps operation will be achieved by adding another power supply. So we are also upgrading horn conductor cooling. So and by adapting a water-cooled slip line. So water tube is embedded in this aluminum plates. So this shows a temperature simulation, which shows a reasonable temperature even at higher beam power. So we also need other upgrade items. So radioactive water disposal. So this current limitation is size of dilution tank. So we will construct a new dilution tank with larger size. So and now, so new building is being constructed here. So and also cooling capacity should be improved. So current capacity is 1 megawatt, but we will need improvement. And also, so for beam monitors, so new beam profile monitors are developed for high intensity beam. So this is a schematic picture of the new beam monitor. So we inject a nitrogen gas into the beam vacuum pipe, and so beam is intercepting this gas, and that creates a fluorescent light, which can be detected by a photon detector. So we performed the first beam test, and we observed the signals, so which is a reasonable result. And also a control DAQ system will be upgraded for 1 Hertz operation. Okay, so this is timeline. So 1 Hertz operation will be done. So after long shutdown in 2021 to 2022, and also radioactive water disposal will be upgraded. And another upgrade period is around 2025. So which includes water cooling upgrade and target upgrade. So, but for the later upgrade, so this installation plan is still under discussion. So we aim to perform this upgrade in 2024 or earlier. So finally, I briefly mentioned about the international cooperation of the high power Newton beam. So there were 3 major accelerators, so in Asia and North America and Europe, and so 3 Newton beam lines. So and the good relationship.
So
yeah. Yeah. So this is
for time and you almost used up. So please be a little bit quick. Yeah.
Okay. So yeah. So I want to say about the high intensity Newton beam cannot be produced only by single institutes. So many inter collaboration, so cooperation is needed. So but we are now doing the cooperative research. Okay, so let's summarize, but yeah, I will skip. So that's all.
Yeah, thank you very much for this Tetsuro, for this important talk of high power beam. Questions from audience?
May I make a naive question, perhaps? Because it's really amazing this all this architecture to get these neutrino beams, but obviously you're always producing a muon beam, the muons, but those muons they are just dumped and let's say wasted, or are they used for any other purposes? Yeah, because
so
basically before about the muons.
So muons are almost dumped, but we are using this muons, so tertiary muons, for the to monitor the beam.
Yeah, this is how I understood it. But is there not any physics use for these muons? Are they useless, or can we do some? Could we do some physics also? Yeah, I'm just thinking about the very nice talk by Angela.
But
this nice muons.
This is very broad muon beam, so I think for physics experiments it's hard. But by using these muons, so we are now developing many monitors. So at this muon monitor pit. So
okay, so due to the time limitation, so we will stop here. So thanks again, Tetsuro, and
thank you very much.
All the speakers in the first block, and we will go back 25 minutes later. And in the next block, we will have CERN for analog, Awake, XFEL, and ALIMA, and MDI. So please be sure to come back to join the session. Thank you. See you.
Hello, everybody. This is Daniele Margarone speaking. I will take over the next block. So for the speakers who are still here, we can use this time to check technically if everything works.
Hi. Ciao, Daniele.
Ciao. I will also put my video on. Yes. Okay, so Alfredo, I can see you. So if you can start.
So I'll share the screen, right?
I can see you. You can share the screen now, please.
I share the screen with you. And I'd like to go straight on the, okay, this is my talk. So should I put the full screen for you?
I don't see your screen at all at the moment, actually.
Okay, very good.
Only your video.
I push the button, share the screen. I just pushed the button and I got into Zoom. I just see Zoom.
I think once you push the button, you should see different windows, and you should choose the one you want to share.
Okay.
Windows. I don't know.
Okay. I see many windows. I see.
Yeah.
Okay. And I push on the one with my presentation.
Yes. Now I can see. Can you try the full screen, please?
I'll go full screen on the presentation. That's it, right?
Perfect. Can you move one slide? Yes, fine. I can also see your cursor, so you can also move the cursor if you want to indicate something. Perfect. Thank you. Great.
So it works. Okay. So so you'll be introducing me like a standard.
Yes.
Okay.
I will say a few
good.
words at the beginning. So if you can stop sharing, we will check the next speaker.
I will do that now. I ask from here. I go to Zoom.
The next.
I stop sharing. Okay.
Perfect. Thank you. Thank you. You can.
Thank you, Daniele. Thank you.
You can stop your video and mute your microphone. Also, thank you. Next speaker is or next test will be done with Giovanni Zevi della Porta.
Hello, that's me. Can you see me and hear me?
Yes. Ciao.
Ciao. Let me share what I want to show.
Yes,
you
I can see it.
And then
yes.
I go here. Oops. And I move slides.
Perfect. I see everything, the arrow, everything. Okay, very good. I can hear you well. Thanks.
All right, thanks, bud.
Good luck.
See you in a bit.
Okay, then let me also ask Alexander Molodojensev if he's there to test his presentation. Probably is not there yet. So let's try with Francesco Schillaci.
Yeah, I'm here.
Yeah. If you can try also the video, if you want to share the video. Yes.
Can you see me? Okay. So I will try to share my presentation. Is it visible?
Coming. Yes. And move one slide, please. On. Perfect. Okay. I can see your hand also. Perfect.
Okay. So I'm stopping the sharing.
Yes. You have time for coffee.
And cigarette.
Okay. Next, Lori Neve. Sorry for the pronunciation. You should tell me.
Hello. Yeah, Laurie Nevy.
Nevy. Okay.
Yeah.
Nice
Thanks very much. Okay. So hopefully, yeah, you can see. So can you see the slides?
Yes, perfectly.
And yep.
Perfect. Fine. I can see also the cursor, so you can use it during the presentation.
Okay.
Perfect.
Perfect.
Thank you very much. See you soon.
See you soon. Thanks.
And again, I apologize for the pronunciation. How are you, she? Are you there? Not yet. So Alexander Molodojensev, are you there? Not yet. Okay, I think they will come in a few.
Actually, I already tested the presentation in the beginning of the previous session.
Okay.
Should work.
Only Alexander is missing. Thank you. Thanks.
By the way, I'm Peter and I am your Zoom assistant. So if you need something, I'm here.
Very good. Thank you very much. Peter, just to confirm, before we start, I will have the rights also to mute speakers in case there is someone.
You have them already.
Oh, thank you. Great. Yes.
So if everything is tested, I will put the waiting screen.
No, it's not everything tested. We are missing Alexander Molodojensev, one talk, 1001. So please wait a few minutes. Because I think you said that Dr. Shi has tested before earlier, right? Yeah.
Yes, exactly.
Yeah. So only one we are missing. I will actually. I can try to reach him in person because we are in the same building. Alexander Molodojensev, are you there? Okay, not yet.
Daniele.
Yes, Alexander, I can see you now. Perfect. I will be connected here from my office because I have everything here.
I will try to share the screen. Just
yes, please.
So screen share. So you see.
Share the presentation, please. Not your personal email.
Yes. That's not personal. Okay. Okay. Do you see that?
Yes. Yes. Can you go full screen or presentation mode?
Yes. Yes.
Very good. I can. And the one slide change. Like next slide, please.
Okay. Yes.
Can you? Yeah. Perfect. It works. Thank you, Alexander.
Yeah. Okay. So
stop sharing video, everything, and I think we.
Right.
Yeah.
So what I can see that I need to enter using my also family name because I just put Alexander.
It's too common.
Yeah.
No, it's okay. It's okay. I will introduce you, so don't worry.
I can rename easy. Okay, I will rename. So one moment.
Perfect. Very good. Thank you. Thank you. So you can stop sharing the video for now.
Yes. Okay.
See you later.
And leave. I will leave the room. Okay.
No, don't leave the. If you want, I think stay online, but stop video.
Okay. We'll use the same, let's say, room for meeting.
Yes. Stay there. Stop video and mute your microphone, or I can mute it. Okay. Perfect. Thank you. So Peter, I think we checked everything. So if you want to put another screen, you are free to do that.
Done. See you in a few minutes.
Okay, great. Thank you. Okay. Hello, everybody. So since we have a few minutes before the recording will start, I would like to use this time to remind you a few technical details. So the audience, both speakers and participants, should mute themselves unless they're speaking, of course. Participants should say their name before they ask a question. And the alternative, they can post questions in the chat box, but this is not preferable because it will make some noise. So please raise your hand, and then I will ask you to speak. Yeah, I would like to remind all the speakers that they have in total 20 minutes, but in fact 15 minutes for the talk and 5 minutes for questions. So please try to fit within 15 minutes, and we can use then we can have plenty of time for several questions. In case there will be too many questions, I would like to remind you that the session will stay open 1 more hour at the end. So please stay, and you can use this time to have additional questions. The speakers, it is recommended the speaker will have their video on, but this is not mandatory. So I leave it to you. It would be nice in the virtual conference to see each other, but if not a must. And I think that's it. So probably Peter will start recording. Peter, may I ask you if I should record myself in the computer?
I will do it.
Okay.
I will switch it on just now.
Thank you. Okay, so 2 more minutes and we will start the block, the last block. Okay, and welcome again. My name is Daniele Margarone from Eli Beamlines, Institute of Physics of the Czech Academy of Science here in Prague. And I would like to introduce the last but not least block of our parallel session on Accelerator. So during this block, the main focus will be on emerging compact acceleration schemes and technologies, along with powerful numerical simulation tools, and also including an exotic introductory talk on the need of a CERN for analogs by Alfredo Iorio. Well, I think this is those are quite interesting topics. So I expect from the audience a lot of questions. So now I will leave the floor to Professor Iorio from Charles University, Prague. Please.
Thank you very much, Daniele, for the introduction. And here is my technical skills. Let's see if I understood everything. Can you see everything? Hello?
Not yet, only your video at the moment.
Only myself.
Yeah.
Okay, so I have to go on Zoom. This is where I see the transparencies, right? This is my slides. Now you should see it.
Yes, yes, okay. If you
okay,
then you can start.
and I make full screen. Let's see. Okay,
Very good.
Is it okay like that? You see what I see probably.
Yes, yes, fine.
Okay, so it is indeed a pleasure and a challenge for me to be here. I actually choose to be here. I was asked to be in the formal theory, but I said, no, I want to be here because I want to foster this idea of a actual construction of a facility where we can test new physics by using analogs. Let me go. I have 15 minutes altogether, so I have to rush. So what I call here Helios is a name that is a long while now. It's about 3-4 years. It goes among our collaborators to indicate this facility. This thing at the moment is a sort of an ideal place, and we use this acronym Helios, which, as you know, is the god of the sun in Greek. That stands for High Energy Laboratory for Indirect Observations. The plan of the talk is the following. I will just briefly say well, everything will be brief. So I will tell about the work of our group and how essentially this idea came about, and the importance of analogs and why analogs are good to probe new physics. Okay, and then I'll try to focus on Helios in particular for the scientific goals and the practical issues. Okay, so our group at Charles University is focusing on a specific analog, which essentially, I may say, is our invention in the sense that it's a material which is super well known, and of course the credits for the discovery of the material goes to Andrei Game and Kostas Novoselov. But what we have done over the years, and I'll show you a list of papers in a moment, was essentially to understand how to manipulate this material to simulate, let me say, situation that we should encounter near black holes or near what people call quantum gravity scenarios. Okay, the group I'm talking about these days is quite populated. These are two postdocs. This is my closest collaborators, Pablo Pais, who's now a senior postdoc in Chile. This is our most recent acquisition, and a student, and probably some of you will recognize people from the that have been employed there at the laser facility there in Prague, okay, and all the people that collaborated over the years. And unfortunately, kind of recently, this young collaborator left us. In any case, this is the group. So it is a very active group. The work initiated with these papers here in 2010, 2011, where we have realized that graphene can be a very fruitful place where to test these fundamental ideas. Okay, and then he went on, and you see here, we will record this lecture, so you will probably have time to go through it if you want. And there are many papers. You see that the number of papers of the last year is growing kind of exponentially. So there's a lot of activity in this area. But this is why essentially I qualify, and I hope to qualify to say a word about this idea of Helios. Okay, there are of course many other analogs, and let me now move to the next topic. The next part of my talk, which is why analogs are important to probe new physics. Okay, so besides the wonderful machines that you'll be talking about, you have been talking about in the section, another section in this beautiful conference, I humbly ask the community to think about considering also this very, much less costly facility where we can try to probe new physics. But why is this interesting? Well, I have to still make the case because this is somehow still the case. And you saw Richard Feynman in the introduction here, because you can take the road from very far away. You can go back to Kepler, but I like to take Richard Feynman as the contemporary father of this line of research. Essentially, we are accustomed to use these three members of this family in our analysis of physics, okay, in our understanding of physics, which is symmetry, duality, and correspondence. Okay, symmetry, you make a transformation, you send your fields to a set of new fields, the action does not change. This is a symmetry, and we know everything about it. Okay, spontaneous symmetry, Brick, the Higgs mechanism, and so on and so forth. Duality is a sort of newer idea, but not that new anyway, where you send fields into a dual, but you don't get back the same action, but you get a dual action. We know how to deal with that. And in this area, the famous, now very well-known idea of ADS-CFT correspondence was born. So we are accustomed to that. What we are less accustomed, at least in the world of pure high-energy physics, is the fact that sometimes equations present a very common structure, which is what we call analogy, and no underlying structure is considered. So Feynman was, in a famous lecture that I will cite in a moment, realized that, okay, and looking at this equation, this very same equation up here, which is the equation for electrostatics, okay, he realized that the same equation holds for other systems: the flow heat, the stretching membrane, the fusion neutrons, irrotational fluids, illumination plane, and probably you can keep going, okay. And he says this beautiful word: so whatever we know about electrostatics can immediately be carried over into that other subject, and vice versa. Okay, so we know about one and we extend this knowledge to the others. In this case, the list of others is here. Okay, but then he went on, okay, and he said, why is this happening? Well, why the equation for different phenomena are so similar? You know, the Feynman has this beautiful power of imagination that can bring him very far away by using simple considerations. And by using the simple consideration, he came up with this idea that everything there was similar because way of simplifying things, he called axons. So he said there must be the real world consists of these little axons, these fundamental objects, okay, that can only be seen at the very tiny distances. Why I say that? Well, because then much, much later, forefront research, which is a quantum gravity we really want to probe and where we expect an enormous amount of new physics, came up with similar ideas by looking at black hole physics. Here, you see the famous Bekenstein bound says that the entropy of any material system must be bounded from above by the entropy of a black hole. Okay, led Bekenstein and then all the family of quantum gravity people to positing the existence of a level X. Okay, so actually, by the way, they use very similar wording. So the idea in images is that it's not just that all these 5 cases that Feynman considered were analog to electrostatics, but that electrostatic itself, along with all of them, is pointing to something which is in common. Okay, so this is something we want to bring from this general idea of why analog systems are important to probe fundamental physics already at the level we're talking about. If you want some further readings, I really suggest to read the famous lecture by Feynman in his. It is the book we all know about. Okay, the Feynman Lectures on Physics, Volume 2, Chapter 12, which is called Electrostatic Analogs. Everyone knows, well, or should know, at least the famous sentence, same equation, same solution. But this is just the beginning of the chapter. Please go through all of it, and you will be amazed. You may agree or not. It's a different topic. And then I suggest some further reading by Jakob Bekenstein, a paper that I wrote on those philosophical issues, let's say, and then a paper written by a philosopher, essentially is taking my things here and is enlarging the philosophical analysis and pointing to the necessity of looking for these fundamental things. So why Helios? Well, Helios, I said what I mean by Helios, and why I dared to be among you. I could say the real physicists, those who actually put their hands in the things. Okay, I'm the theoretical guy here, but I like to talk very much, as some of you in the audience know, to experimentalists, and I think that really I would like to make the case for this facility somehow. So I say that the goals here are the scientific goals that you see here. It's the second scientific goals are of 3 kinds. Okay, to find axons. I mean, what I say by this sentence, you see, is under quotation. I mean that we can look for the fundamental guys, so for the very new physics, even at this level of energy. We don't need to go. Of course, it would be great if you had an accelerator of the size of the galaxy. We can actually probe certain energies. Well, we cannot. Okay, so we have to be content with the fact that this thing can be in principle done. But we still have to do some theoretical work on that, and we have to systematize this thing. And here I cite a beautiful work of my former supervisor, my PhD supervisor, which is the late Lachlan Rafferty, who he's been among the inventors of supersymmetry, so a very theoretical person, but he didn't let me say, he liked these things of the analogs, and he found a duality transformation that would connect supernova explosions, the real supernovas up there, with the implosions in plasma under intense lasers. Okay, so he found a precise connection in that, and then all the physics that most of the physics that you could see from the plasma under intense laser will be translated under this duality to the physical supernova. So this stuff is to say that one of the goals of this place, scientific goals, would be to actually look for the fundamental guys and systematize and put analogs in the right place in this family of well-known theoretical tools like symmetry, duality, and correspondence. A second thing, which is somehow more practical, still very fundamental, is to focus on very important debates, open issues. Okay, one of the most, as you probably all know, one of the most important issues open out there is the occurrence or not of information loss in black hole physics. Okay, you know that the history is super long, but it can never be closed because there is no experimental evidence. Okay, here I summarize this by this picture, which is a famous page carve of the evaporation of a black hole. And here the question mark is, if this carve, which is how the entanglement entropy evolves in time, ends up to zero, there will be no information loss. If it ends up somewhere up here, there will be information loss. Can we envisage experiments? Okay, can we move from the kinematics of a Hawking phenomenon, which is a kinematical phenomenon on a black hole, to a dynamical? So this is another challenge that Helios should face. And three is a sort of a didactical. So I'm also teaching sometimes. So I became aware of the importance of saying things properly to the students. And I think that those young guys who went into pure theory these days are missing the idea of what they say can be tested in experiments. Okay, of course, if you work on supersymmetry, strings, loop quantum gravity, and all this business, let me say, you grow up with the idea that your stuff could never be tested. Well, I think this is not true. In Helios, you could do that. Okay, you can you can always find an analog where some part of what you say can be seen experimentally. Okay, and actually here I put this very famous equation of the so-called Virasoro algebra that for those who are not aware of that, this is a very fundamental object that is found in many places, which I cite over here. Well, we can find actual shapes that we can make in a lab. Okay, so I read here that the connection is not stable. Hope you can still hear me. Now the practical issues. The practical issue on why Helios is important. Well, we would have really a cross-fertilization place at work, because we would have condensed matter people, high energy physicists, all together, all working towards this goal. And you never know what can come up. Okay, you would like to make a black hole, but while you're trying to make a black hole with graphene, you may end up doing a device. Okay, and it would be a wonderful place. It would be a wonderful place because if you have a theoretical idea, you can go straight to the experimentalist and ask him or ask her to do it. You will learn. It will be a fantastic place for cross-fertilization. And I say, borders are the borders will be all removed. Okay. In my personal opinion, this is something that could be built in the same spirit of how the ICTP of Abdus Salam was started. I have also a practical. Okay, this is my own. Let me say wish. But there is also a practical story here, is the fact that since it will not need a titanic technological effort to be done, okay, this is something that could be done also in non-super developed places, okay? At the end of the day, we have to put next to theorists some condensed matter facility, which usually is much less costly than other facilities. And about costs, let me now just give you the last sentence. I hope I manage to stay within the 15 minutes. This is a transparency, a slide that was given to me by friends working in CERN. And this is the budget of CERN, which is, of course, all well deserved. Okay. But let me say that for a start of our thing, I didn't do a proper calculation, but we will be super happy if we get this tiny fraction of the 2012-18 budget. Okay, this 53 million will be super good for starting our Helios, and it will be just a tiny fraction of what CERN is actually using for its running, its standard running. And okay, that's it. So I can close here, and I'm ready for questions. Unfortunately, I will not be able to stay after my talk. But so if you have questions, I'd like to take them right now. Thank you very much.
Thank you very much, Alfredo. Very interesting, futuristic talk. I hope it will be in the close future. Okay, so the session is open for questions. I do not see any hand raised yet, so maybe I will start, and then you will have 1 more minute to think about your question. Alfredo, you mentioned the sentence from your supervisor about lasers and plasma. As you know, I am a poor experimentalist, so I will ask you an experimental question. Do you have already an estimation or rough estimation of the laser intensity and plasma temperature that you would need to do something which is already interesting for analogs?
Okay, so in the for this particular case, I have no idea. I just remember this happened in 2001, as you may see from here, where I was still studying with O'Reilly. What I know of this particular situation is that these people were measuring some certain transitions with like critical exponents, and they were measuring this critical exponents of this phase transition and had no idea why the critical exponent came up that number. I don't know, 2/3 or 3/4, I can't remember. And by using this duality that they found in there, they actually were able to predict precisely this number. So that's why I cited this as a case where a very precise theoretical argument can set up a super precise correspondence. As for your question about the specific, let me say, the specific characteristics of the lasers to build something useful for analogs, so perhaps you might remember, we've been interacting with Tazio Levato, Marcelo Ciappina, and other people there from LA Beamline, and our understanding, we have now recently published a physical review on the topic, and what we have understood in that case is that more than the power itself, what is very important is to have a high control on the harmonics. Okay, so these days there is a lot of study on how the laser interaction with the graphene, actually the graphene itself, can generate high harmonics. And this is super important for us because, as you know, the generation of higher harmonics goes into the nonlinear regime very much. Okay, and these will essentially find a window of where to look for the analogs. So to answer your question, we don't focus very much on the intensity, but rather on the frequency part. And the good news for people like me is that there is a high control of these frequencies, and this is super important. Let me give an example. Let's see. I have very little equations here. I don't know if I have anything. No, I don't have anything in here. I don't want to go into the computer and show you. Okay, so you can think of this fact. Okay, what I need something that simulates a gravitational field, but it's not a gravitational field. So if you want to do that, then you need a potential. Because when you write general relativity, we all know it's a curvature of space-time. But curvature of space-time, the most important bit is the time part, the G00. So the clock that goes with frequencies that you can tune. Well, if we can do that, we can really, let me say, that we can really have a control on how this laser will simulate the gravitational field. So this is the more than the intensity, this is where we're pointing. And if we're able to do that, we will have a very nice device to simulating essentially any kind of gravitational field.
Okay. Thank you very much. We have time for one short question. If not, let me thank the speaker again, and we can move to the next speaker. So Giovanni Zevi della Porta, he will be reporting on highlights of the Awake experiment. Alfredo, if you can please stop your video. Very good, thank you. Giovanni.
Hello, can you hear me and see me?
Yes, now yes, okay.
And my slides are okay?
It looks perfect. Go, please.
All right. So, hello, and thanks for inviting me and Awake to present our recent results and future plans. We're very happy to be here, even if it's virtual. I will start by introducing what the principle behind Awake is. Then I'll show you the most important results of our first run. This is all quite recent. What we're preparing for our next run, and then what we're thinking about to go beyond. So the principle behind Awake is plasma wake field acceleration using a proton driver. And this requires several steps. So I'm going to try to go through them in this cartoon. First of all, we use laser pulse, which is red here, to ionize a gas forming a plasma. Then a proton bunch, which is our driver, generates wave fields in the plasma at the plasma resonant frequency. And because the plasma resonant frequency, the plasma wavelength is smaller than the proton bunch, then micro bunches are formed. Essentially, the structure of the proton bunch changes. And then these micro bunches act coherently to generate wake fields. And if we put electrons in these wake fields, the electrons are accelerated and also focused. So this is what we're trying to do and what we're trying to prove that is possible. Now, why do we want to do this? So these are the two most important questions that we want to that motivate our experiment. Or why do we use plasma instead of a superconducting RF cavity? This is true for all wake field acceleration. The idea is that plasma can sustain higher fields, so more megavolts per meter, leading to shorter and therefore hopefully cheaper accelerators. And then a nice property is that plasma is actually self-focusing. So it provides not just accelerating, but also focusing fields. Then why do we want to use protons? Awake is the only plasma wake field accelerator that tries to use protons. And the idea here is that protons are the beams with the highest stored energy per bunch currently available. Of course, and they are already available at several facilities, mostly CERN, but not only. And so if we can use existing proton beams to reach the energy frontiers with electrons, it's a win-win. We don't have to build the driver accelerator. And we also don't have to use staging of several small steps to get to the high energy, which would be required using different drivers. So this is why we're doing it. So what is Awake? Awake is a proof of principle R&D experiment to see whether this accelerating scheme can work. It's made up, it's fairly big, it's more than 20 institutes and 100 people, and it's fairly recent. It all happened in the past 10 years. It's installed in the CERN Accelerator complex on a proton line that comes from SPS, and that used to be the CERN Neutrino to Gran Sasso, see the TNGS line. And now that experiment is over, and so Awake lives here. What does the experiment look like? Well, the elements that I've shown before, we have to have a laser beam, we have to have a low energy electron beam to drop the electrons in the wake fields. And then of course we have to have a plasma source. We have a 10-meter long rubidium vapor source, which is where the plasma is formed. And we have to have the proton beam drive the wake field. And then after the plasma source, we have all the diagnostics to study the electrons. So the sequence is what I was saying before. So we have the laser ionizing the vapor, forming the plasma. Then the protons come in, microbunches are formed. The microbunches form wake fields, and the wake fields can accelerate electrons. So going straight to the most important results of run one, which is why we are optimistic and why these studies are continuing, and this project will continue for the next several years, is that in run one, first of all, we showed that self-modulation actually takes place as predicted by simulation. So in the bottom, so this plot shows actually streak camera images of a proton bunch without the plasma on the top and with the plasma on the bottom. And you can see with the naked eye, essentially, looking at the picture, that the microbunches form. Not only that, but the frequency of the microbunches follows the expectations, the expected dependency on the density of the plasma. So this process takes place in a way that we understand. And then, of course, the second milestone, which was achieved only a couple of years ago, is acceleration. So the money plot is on the left. You see an actual picture of the spectrometer where the position in the spectrum of the spectrometer is converted into an energy. And so this is a single shot where you can see that the electrons had a much higher energy than the input energy. And then we also studied this in terms of, again, the density of the plasma and the profile of the plasma, showing that we can reach energies up to 2 GeV from a starting energy of around 20 MeV. The maximum accelerated charge was reasonable, but in terms of percentage, it was actually quite small because this was really a proof of principle R&D to see whether this was possible at all. And you notice I'm not talking about emittance here because we didn't even try that, say, in the first run. And so these are the things. And then there's much more scientific output of run one, which I don't have time to show. But the idea is to, we have a lot of data to understand self-modulation and acceleration. And we have produced many conference presentations, proceedings, and papers, some of which are linked in the backup. So what are our plans for the next run? The idea here is to be much more ambitious. So not just accelerate electrons to high energy, but also preserve beam quality as well as possible. And at the same time, develop plasma technologies which can allow us to go from our current 10 meters of plasma up to 100 meters or so. And so the Wake Run 2 cartoon looks like we have a lot of doubling, mainly because we are separating the self-modulation process in the first plasma and the acceleration process in the second plasma so that we can control the two separately. And then in terms of milestones, we want to first focus on the self-modulation and again, have better control. So instead of self-modulating only part of the proton beam, as was done in run one, we want to self-modulate the whole proton beam so that there is no head of the proton beam which can cause interference. Then we want to make sure that the self-modulation is stable, or that it stops growing at some point. Because if we don't do this, then the self-modulation process, which is coming from an underlying instability, can actually destroy the wake fields for very long accelerators. So this freezing of the self-modulation is achieved through a density profile, which we will be able to do in run two. And then, of course, the obvious goal is acceleration and emittance preservation and small energy spread. And here are two plots. The left one is showing the electron beam following the proton beam. And in the right one, this is a complicated plot, but if you look at the orange, so the y-axis on the right, and the orange line, you see that given a delicately chosen set of parameters for the incoming beam, so both transverse and charge and profile, we can get into a situation, at least simulation tells us we can get into a situation where the emittance is preserved even after 100 meters. And so this is what we want to achieve. At the same time, in parallel, we have to develop scalable plasma sources because our current method, which is laser ionization, doesn't work for plasma sources much longer than 10 meters, and we want to go to 100 meters or more. And so we're following two different paths. One is a helicon, and one is a discharge plasma, and hopefully at least one of them will give us a technology that can get us the plasma we need for a long accelerator. So if this all works and run one was a success, if run two works as well as run one, then we can start thinking about, okay, so what can we do with high energy, high charge electron bunches, and can we really switch from electron R&D to particle physics experiment? And of course, one would want to go straight to an E plus E minus collider or very fancy concepts, but we want to be a bit more realistic, and we want to start from things that we think we can do, even with the current, with small updates to the current setup. So the first step that we considered is producing electron bunches for fixed target experiment, because this has the least stringent requirement, and it could take place. And so we've started studies based on doing this at the current site, just by extending the plasma cell and seeing what can be done. And then the second step is, since we're always producing these electron beams at proton machines, then we could create an electron-proton collider or electron-ion collider. So I'm going to go through quickly these two possibilities. So the first question in terms of electron bunches is, what kind of electron bunches could we make if run two works and we can have a plasma of order 100 meters, then these are the charges and energies we can achieve, and also the number of the electron on target. And it turns out these are actually quite relevant. If you look at what the reach of a wake would be in terms of a dark photon search or a strong field QED test, then you can see that not only it's reaching beyond the current limits, which are the gray area here, and the purple on the right plot, but it's actually quite competitive with many of the future planned experiments. So it would be quite relevant to do that if we could. Then going a bit more ambitious, the idea of re-injecting this electron beam into the proton collider and colliding electron-proton, then we have alternative schemes to what we've heard about this morning, the electron-proton collider. One is a little bit less ambitious. So PEPIC would use SPS protons to drive electrons and then inject them and collide them with LHC protons. So this would get a square root S of 1.3 TeV. And then much more ambitious, of course, driving electrons with LHC protons. This would give us a 3 TeV electron and a root S of 9 TeV. And of course, and the exercise was also done at the other proton facility we have, not at CERN, which is RIC. And here again, it was shown that in principle, the same technology could be used to make an 18 GeV electron beam for RIC EIC. In terms of reach of these machines, I'll just show a few plots. These are the classic deep inelastic scattering plots showing what the very high energy electron proton collider could reach with respect to HERA, and of course PEPIC, which is driven by which is a little bit less ambitious, would be somewhere in between. And in terms of leptoquark searches, here again we have leptoquarks which would decay back to electron jet or neutrino jet, so would have to be detected. We made a simulation looking at the expected backgrounds after some very simple cuts, and based on the number of signal events expected for different strengths of the coupling constant, we can see that the reach of such a machine would be much beyond the current LHC limits, which are at about lambda of 1, which are about here, lambda of 1 for a few TeV. So putting this all together, it's wonderful that Awake Run 1 proved that we can accelerate electrons using protons, and that self-modulation works. And this is very encouraging for Awake Run 2, which becomes more of a technology challenge and engineering challenge to preserve high beam quality and to develop scalable sources. And so we're optimistic, cautiously, that we can go from accelerator R&D to particle physics experiments fairly soon. And of course, we've looked at a few things, many more could be looked at. Of course, I hope I've convinced you that there's already several interesting applications of the order 50 GeV electron beam, which we could have in a few years. Thanks again, and please ask any questions, and please email me if you have questions you want to ask afterwards. I didn't set up a Mattermost channel, sorry.
Thank you very much, Giovanni. That was very nice to hear about these promising results. Looking forward for the next campaign. Well, I would like to ask the audience, if you have any question, please go ahead. Again, I don't see raised hands, so I will start, but please try to ask a question. Maybe Alexander wants to ask a question?
I am preparing, no.
Okay, so my question is the following. I come from the laser plasma community, so not so far from this. And the typical question I am asked is, plasma is an unstable, by definition, unstable medium. So can you comment on, qualitatively, can you comment on how plasma instabilities could affect the quality of the electron beam in terms of energy, for instance, or pointing stability?
Yeah, no, good point. So, well, there's two. The first answer is not directly to your question, but I think it's still relevant. Is the fact that plasma is unstable in terms of remaining plasma because it recombines, and so the fact that the repetition rate of a future experiment will be limited by how quickly the plasma recombines and whether we have to wait for this recombination before creating more plasma. This is something we're studying, but I think you were asking more about instabilities that the plasma causes, for example, on the pointing. One thing that comes to mind is hosing, the hosing instability, which is something, I don't have a plot here, but essentially what happens is if the beam is not perfectly centered, then the plasma starts moving it around and yes, really doing this. And so this is something we're actively studying, and we have a lot of data in Run 1 where we have looked for hosing, especially because it's predicted by simulation, so we expect it to happen. But as you know, the correspondence between simulation and experiment is hard to achieve, especially on such a long plasma, because 10 meters are difficult to simulate. So what I can see, what we have seen, and most of this is published, but what we have seen in Awake, in our experience, is that this instability, the hosing instability, is hard to get to. Rather than, so we actually have to intentionally misdirect the beam and intentionally misalign the proton and the laser beam, for example, in order to get a hosing instability. Otherwise, we don't see it. So in our current experience, this is not something we are super worried about because it hasn't showed up as strongly as the self-modulation. And with instability, it's always a game of which instability wins. So in principle, We have self-modulation instability, which we like, and the host, because it creates the microbunches, and the hosing instability, which we don't like. And it turns out that the self-modulation instability is much, much stronger than the hosing one. So in the regime where we have looked, it wins. Now, for 100 meters of plasma, I don't know.
Yeah, especially for the high energy, if you want to do collision experiment, this is an important point, I think.
I agree.
Time for one short question, additional question? No? Okay, then thank you again, and let's move to the next speaker. This is Alexander Molodozhensev from Eli Beamlines.
Yes.
So, Alexander.
Oh, yes, I will share my screen. Hello.
Share your screen, yes.
Share screen. Yeah, do you see the screen?
Yes.
Okay.
Please go ahead.
Can I start? Okay. So, hello, everyone who joined this session. It's very nice to make this presentation because, in principle, from my point of view, we are right now at a very interesting way to develop a laser wake field accelerator. And I will talk about new generation of the compact XFL based on the laser wake field acceleration and current development and at ALI beamline and future perspectives. And how can I move it? Sorry. Okay. So it's content of my talk is I will just mention about Linux-based FEL current status, and after that I will concentrate on the laser wake field acceleration, the current achievement and limitations, and I will also summarize some main challenges which we need to face if you want to use laser to accelerate electrons for FEL. And after that, I will talk about the compact laser-based FEL at ELI beamline and like a whole research program, which is based on the laser development. And we have some program to go from incoherent to coherent photon radiation. And finally, I will tell about the next plan beyond like a 5 years scale. Just to summarize the current achievement for Linux-based FEL, we can look at this page, and you can see that in principle, right now in this field, we moved from very nice, great physics to great technology. And as a result of this development, around the world right now, we have a few Linux-based FEL, and I divided these existing machines in two parts. It's like a soft X-ray facilities, like a Flash and Daisy Fermi in Italy, and hard X-ray, like a European XFEL, LCLS and SACLA in Japan, SFISFEL in PSI, plus I forgot to mention about the Korean XFEL. But we can see that in principle, if we are talking about soft X-ray, the required energy for electron beam is just 1.5 GeV. In that case, we can generate the photon wavelength from 4 up to 100 nanometers, and pulse energy will be around 100, 300 microjoule. In the case of hard X-ray, the energy should be much bigger, from 8 to 17 GeV for existing machines. And in that case, the photon wavelengths can be even less than 1 nanometers. But what is our main components for the existing machines? And we can see that what we need to have a bright electron source. We need to have a Linux accelerator for Linux-based machines. After that, we need to have bunch compression system because the bunch length in Linux is quite long. And after that, we need to have antilateral section, photon beam lines, experiment lines. And the total footprint for existing machines, if you are using Linux as a driver for electron beam, is quite large. It's from 300 meters up to 1.6 kilometers only Linux. Plus, we need to have a quite long undulator section, which could be a few hundred meters. But at the same time, you can see that XFEL opens a very nice, very bright future And when we start using XFLs as like a fourth generation of photon sources, brightness of the beam, photon beam, jumped significantly. And now the question is, what could be the next as like a future XFL, which is very required from the point of view of the users. And now we can just review what we have. So we have RF acceleration, and we know that RF acceleration is very nice established technology, and it has a very long history starting from the electrostatic acceleration. After that, Widerøe suggested to use a resonance accelerator, and all this kind of very nice physics now implemented into existing Linux machines. But this machine has a quite significant limitation. We cannot increase the accelerating field up to some limit. And the next question is, what can we use to overcome this problem? And in principle, plasma wave field acceleration is a very nice candidate to proceed. And we have very great physics, starting from the Vexer proposal. And now also we have a very nice, very promising experimental results in different labs. And now we're waiting when new technology will come. What we can get if we are using plasma wave field acceleration. In principle, experimentally it was demonstrated that we can achieve 8 GeV using laser wave field acceleration in a discharge capillary. And even more, we also have experimental achievement which is connected to multi-staging. So it means that in principle, we can use a different, a few accelerating structure to accelerate electron beam up to a few GeV. You can see that in principle, using 2 capillaries, we can get even 10 GeV. That's a very interesting way to go. Now just let's review shortly history of the laser wave field acceleration. And as I said, basically the first idea came from Wexler in 1956. And after that, 1979, Tajima and Dawson introduced concept of the laser wave field acceleration. And it requires a very short, intense laser pulse. And this pulse should be injected into the plasma with appropriate density. But at that time, the laser itself had some kind of limitation. And all experimental data indicates that in principle, concept works, but energy is limited. To overcome this problem, we can use a chopped pulse amplification, which was proposed by Strickland and Morrow, 1985, and they obtained the Nobel Prize for this proposal. And now we can develop the high power short pulse laser using this technology. And this kind of laser pulse can be a driver to excite laser wave field using a single very intense laser pulse. And we can go to blow up regime. And 2002, we have another very interesting proposal from Puhov and Meyert and Wen. And they started a bubble regime, and it opens also the way to generate high energy, quasi-monoenergetic electron beam without external injection and probing. So that is a very interesting history. Now we need to look at what kind of problem we could have. In principle, we know that laser wave field acceleration has some kind of limitations. First, we have laser diffraction. So it means that actually when the laser propagates through the plasma, the size of the laser spot will be changed. So it means that actually we need to find a solution to extend this acceleration length. Another very important limitation is dephasing. So it means that this kind of problem can be solved by changing the density of the plasma. And next important point is the depletion of the laser energy. And in that case, we need to go to low plasma density. And another also very important item which we need to think, that's a bunch charge limitation, because a bunch which will be injected into the bubble it will change the properties of the accelerating fields by using some beam loading effect. So, but anyway, it's, on this also slide, we can see that in principle, we have very nice experimental results, and they indicate that increasing of the laser power and reducing the laser plasma density, we can go to very high energy. As I said, it's in 2014, the Lehman's team in United States, they obtained experimentally 4 GV, and now even more. They reached even 8 GV. So it means that actually, in principle, this way is very interesting, and we know what to do. So, but let's look at this problem from the other side. What kind of challenges we have if you want to implement this laser-driven FEL? So, and on this table, we can see that in principle, if we have a Linux-based FEL, we need to have energy up to 17 GV. Laser plasma accelerated based FEL, right now we can say 8 GV is possible. Next is RMS energy spread. What we need to have for FEL, we need to have energy spread which is less than 1. In principle, right now also we have for laser plasma acceleration, we have experimental evidence that's in principle by optimizing the acceleration process, we can get 1%. But the most important for FEL is a parameter which calls like a slice energy spread, which is very, very small. It's, for Linux-based FEL, usually they have a slice energy spread less than 0.1. For plasma accelerator right now, we don't have this kind of data. We need to understand how to manipulate the bunch to reduce the slice energy spread. That's problem number 1. And in principle, to face this problem, we need to design the dedicated electron beam transport, or also we need to have a special undulator section. Bunch charge looks like more or less fine. We can get using a laser plasma acceleration required bunch charge. Bunch length without compression, laser looks very nice because in that case, naturally we can get a very short bunch, which is determined by the laser pulse. Peak current looks fine. RMS beam divergence for laser plasma acceleration looks more or less problematic. We need to find some kind of advanced laser technology to provide the small. We need to reduce the divergence of the beam by using the optimal injection scheme. Repetition rate, that's very challenging. You can see that in principle, all existing machines, Linux-based machines, they have a repetition rate more than 30, up to even 27 kilohertz in DESI. And achieved numbers for laser plasma accelerations are around 5%, 5 hertz repetition rate. That's a very challenging, and we need to find some kind of technology for the laser development. And stability and reproducibility. For Linux-based, it's perfect. It's a very nice established technology. It works fine. For laser, still, we need to improve the parameters of the laser to have a stable operation. In the case of stable operation, we have some experience because in principle, we are working in collaboration with Hamburg University. And we prepared the experimental setup, which has name LUX, which also is based on the laser and produce the incoherent photon radiation. And by using the capillary cell, gas cell in the capillary. And using a LUX setup, what we did is we had a 24 operation using a 5 hertz repetition rate, and we reached 400 MeV, and that was a very nice achievement. The similar achievement was done by Flash Forward and DESI, and they had a 72 hours operation using a discharge in the capillary. And what we need also, we need to think about the dedicated electron beam transport development, including the electron beam diagnostic. And the most important that we need to preserve the quality of the electron beam accelerated by laser field. And because in principle, we'll have a very strong effect of the chromatic aberration plus collective effects.
Alexander, you have 2 more minutes for
two more, just 2 more. Okay, it's I will skip some kind of introduction about the ELI beamline, and what I will say that now we have a concept for the laser field acceleration, and according to this concept, what we need to have energy only 1.2 GeV, and it looks like for this energy we can reach saturation after 20 meters. And also right now we are preparing the setup, which is based on the discharge in the capillary. We have we made the simulations to see a gas fill in the capillary. Also, we are planning to use active plasma lengths in our setup in future. And also right now we are thinking about the dedicated electron beam transport, because we need to preserve the parameters of the electron beam accelerated by the laser. We designed the dedicated electron beam transport for incoherent photon radiation, and now we are preparing to set up E5 in our experimental hall. And in principle, we're planning to have also a demo FEL, and in the case of the demo FEL, we will go to water window regime, and if you look at the parameters, we will be very similar to the existing FEL in Italy. And on this picture, you can see the plan which we have right now up to the end of 2022. We will build this setup in E5. We will have 2 lasers, L3 and L2, will come to our setup in E5, and we will produce incoherent photon radiation for user operation. And after that, we will extend our beam line and we will optimize the parameters of the electron beam for the demo FEL. And finally, we will replace compact FEL, compact undulator, and we will use a FEL for undulator for FEL, and which could be also compact, but around 2.5 meters. And also, we're planning to use a seeded FEL. And after that, if we proceed successfully with this demo FEL experiment, after that, we are going to build water window FEL, and all this activity right now is in the collaboration of the Europraxia. And finally, it's shortly, sorry, it's unfortunately no time for detailed presentation, but as a conclusion, I just want to say that the successful realization of the demo FEL project and FEL will open the way to build laser plasma based FEL using a high repetition rate laser. Okay, thanks for your attention. If you have questions, I'm ready to answer.
Thank you very much, Alexander, for the very comprehensive talk. So I will not ask questions this time because we work at in the same project. So I would like to ask the audience for questions. No more questions? No, single question.
I can extend my talk for a couple of minutes.
So that means everything was clear, and we probably can move to the next.
Okay. Thanks.
Yeah. Thank you, Alexander.
Thank you. Yeah.
So let me invite Francesco Schillaci from ELI Beamlines again. We'll be talking about the recently installed ELI-Maya ion beamline. Please, Francesco. Yes.
Is my screen visible?
Yes, I can't hear very well. Can you try to speak?
Yeah, can you hear me now?
Yes, so try to speak loud.
Yeah, okay. Thanks for the introduction, Daniele. I will be presenting basically our ion beam transport line installed in our experimental hall, which is dedicated for ion acceleration. So this is ELI Beamlines building, and we are put on a particular section of the experimental building, which is 2 floors underground, which is the ion acceleration hall called E4. This is a summary of the equipment we have. We will be focusing on the ion beam transport line today. All these equipment listed here are realized in order to provide the user with some beam with defined parameters, which is very well characterized in energy and also in dose from for the last part of the ion beam line. So the user will be able to get a beam that is useful for example, irradiation. Especially, we are focused on medical application, but we are anyway. The goal is to provide the beam for a wide range of users. Any kind of experiment can be carried out. This is how the experimental hall looks like at the moment. So the beam transport is installed. We have a plasma mirror chamber, then the beam goes to the interaction chamber, the target sits here, and then we have the ion beam transport and the symmetric station where the beam is characterized in air and sent to the irradiation point. So we are about to start the commissioning at the end of this month, hopefully. To focus on the ion beam transport line, which here is better described. It is divided in 3 sections. So we have a collection section sitting here, then a chicane for the energy selection, and the last part where the beam goes in air for the characterization. Before describing the ion beam lines, we need to understand how the beam is produced by the laser shots. I think the laser interaction mechanism is not important at the moment. What is important is that a laser accelerator can produce a large number of ions, especially protons. The bunch is pretty short at the production point. And it is, well, in literature, you will find out that the beam emittance is very low. This is actually because the beam is extremely small at the source in size. The size is like comparable to the laser focal port. We are talking about some tenths of micrometers, but the angular spread of the beam, the angular aperture of the beam, as you can see in this plot here, is pretty huge. Also, the beam has a wide energy spread. Basically from 0 to a certain cutoff that depends on the laser, on the target. And this is a nice feature because basically our beam line is intended to select a certain energy from this spectrum and deliver this energy, improving the beam feature to the user. So basically we want to provide, we start with a beam that was emittance looks like that, but we want to provide something that is most similar to a classical cyclotron beam emittance. These are the sections that I will be presenting. We start with the collection section. But before discussing the collection section, we need to understand how we want to select the beam. So basically, it is important to first define the selection method. In this case, the choice is to use a single reference orbit along this chicane, and the orbit is fixed for all energies. So this means that we have to change magnetic field to select the different energies, and this has the advantage that basically the energy resolution is fixed and depends just on the slit aperture side that is set at in the middle of the chicane. So basically, with the standard electromagnets, we can select with very good precision protons up to 300 MeV and carbon ions up to 70 MeV per nucleons. So once the reference orbit of the chicane is defined, we can define how the selection system has to be done. The selection system basically has to inject in the selector the energy component that we want to select. So some constraint on the transfer matrix of the beamline has to be respected, which are listed here. Basically, we want a waist on the radial plane and almost parallel beam on the transverse plane. And this condition has to be fulfilled for a wide range of energy. And the choice is at the end was to come up with a set of 5 permanent magnet quadrupole with a pretty high gradient over a large bore. We are talking about 36 millimeter of magnetic bore here. So the pole, the peak field is around 1.8 Tesla. And these magnets are made by a double array of permanent magnets. The inner array has a higher coercitivity, otherwise the wall array will try to kill itself. And this is so the gradient, the field quality, the gradient uniformity, and the integrated gradient uniformity are pretty high. So it's like high quality field magnet. The magnets are set on a mechanical system, allows to displace, to change relative distance about the magnets. This is the only degree of freedom we have to tune optics for different energies. And also the mechanics has been designed in order to withstand the huge force between the magnets, because they have to be anyway pretty close to each other. Minimum distance between each magnet is around 15 millimeters. The magnets have been characterized with standard accelerator at INFN LNS. This is a comparison between simulation and experimental data for the characterization. So we have a pretty nice control of the beam. In films here, you can see that the beam is a little bit tilted, but this depends on the alignment precision that is possible to reach using optical theodolite, as it was done during the characterization. After the collection system, we already have a definition of the chicane. But before designing the selection itself, we need to understand the emittance growth in the quadruples, because we don't want to lose any more particles inside the energy selector. So you see that these two systems are strictly linked to each other. For this reason, the acceptance of the chicane has to match these numbers here that describes how the beam looks like when at the output of the collection system. This means that we have to design we have to design 4 electromagnetic quadruples with a field that is going from 0.06 up to 1.2 Tesla. Effective length is variation is within 2 millimeters. And the gap is pretty large, because also the beam inside here will be pretty large as well. The magnets are laminated. This is important. I will stress this, the importance of the lamination of the magnets in a minute. As you can see here, the reference trajectory lies within the good field region of the magnets, and these are the magnets installed again at INFN LNS for calibration of the chicane. So basically, we did calibration with different energy using cyclotron and tandem beams. So this is an example, changing field and basically checking if we can send the beam on the nominal selection position, which is 160 millimeter shifted from the reference beam axis. And basically, as you can see in this plot, that is comparing analytic formula, simulation, and experimental data, everything lies on the same curve, so the calibration is pretty precise, and also the control of the chicane is pretty well in my opinion. Regarding the lamination, the chicane can be used also as an active energy modulator. In fact, the lamination of the yoke and the proper tuning of the power supply allow us to change field every second within a range of plus minus 20% respect of the starting point of the field, without any eddy current aspect on the vacuum chamber, so we don't have a high harmonic component of the field producing strange or unwanted aspect on the beam, which is anyway polychromatic beam here. And we can use the chicane basically to deliver for every shot, every laser shot, to different beamlets to the irradiation points, so in a way to reproduce the spread out Bragg peak, which is extremely important for the radiation, also from the point of view of medical application. Then we have the beamline ends with 2 quadrupoles and 2 correctors. These are basically standard magnets. There is no need to spend more time on this, but maybe we can have a look at some beam transport simulation. So just to give you an overview of what we expect to have as a output. So we start with a particle beam spectrum and beam aperture that I showed you before. We try to prepare the setup, for example, for 6 MeV protons. So we start with a monochromatic beam. We set up the quadruples, we set the energy, the magnetic field inside the energy selector, and at the output of the chicane, the beam is pretty nice, and we are losing 80%. So 20% of the beam is still preserved here. Then we can refine further the beam shape using the last part of the beam line. But still here, the beam is monochromatic. In fact, when we go to a realistic laser-driven spectrum, you see here that first of all, at the slit position, the beam is not completely selected. This is why we need 4 dipoles. Actually, for the selection, 2 are more than enough, but we need to disperse the beam twice, 2 more times, in order to have the output, the energy spectrum that we are expecting. This is due to the fact that the large divergence is somehow mixing everything inside the chicane. So 2 more pending stages are necessary. So how the beam spectrum evolves inside the beam line is here. So we start with the exponential tensor-like spectrum. We are losing a lot of particles inside the quadruples. Then at the selection point, the spectrum, as I told you, is still pretty large, but it is clean as we want at the output of the chicane. And here we are, as you can see here, basically in the chicane, we are not losing any more particles within the range that we want to select. But the beam shape is not optimal, as in the monochromatic case. As in fact, you see this star shape, which is kind of memory of the quadrupolar field imprinted in the beam. But this can be further improved using the last part of the beam line, the 2 quadruples we have, and also eventually some passive element on the inner parts to improve the beam uniformity. We didn't start the commissioning, as I told you, but we are already designing high energy and a very high resolution Thomson parabola spectrometer. These are some equations that tells you how Thomson parabola spectrometer works. Basically, it is a simple device. You have an electric field for energy dispersion and for charge separation, and a magnetic field for energy separation. And the issue here that we have a Thomson spectrometer, but it cannot be set on the main line because of the presence of the magnet. But the presence of the magnets allows us to have already a magnetic dispersion sector. So the idea is to use dipole 1 inside the chicane as a part of the Thomson parabola spectrometer, and install inside this chamber a set of electrodes for the charge separation. So yeah, basically the electric sector will be installed inside dipole 2. The challenge here is that the electric gap will be pretty large because we cannot destroy acceptance of the chicane. So we need a pretty high electric field, and this is the reason why we are on the prototyping phases. So we build a mock-up of the chamber. We have a procedure to install the electrodes and the insulators inside the chamber using a pneumatic expansor, and this mock-up will be tested from the high voltage point of view next week. So in case of not major issue, we will go to finalize the installation of the electric field inside the chamber that is in the chicane, and we will finish the preparation of this additional device that we are preparing.
So I've got 2 more minutes.
Yeah, I'm done. This is like a summary of my talk, but I think that probably the most important message is that we are about to start the commissioning. So hopefully within the end of the year, we will be able to receive the first user, let's say assisted user commissioning experiment in the ion acceleration only for. Thanks for the attention.
Thank you very much, Francesco. Again, I will not ask questions time. So time for questions. We can have even 2 or 3 questions. Okay. Nobody asking question. Okay.
Okay.
Then thank you again.
Thanks. Bye.
And let's move to the next talk. So this will be given by Laurie Nivi from Royal Holloway University London on bridging the machine detector interface. Please.
Hello. Hi, thank you. Can you see my slides okay?
Yes, perfect.
Yeah. Okay, thank you very much. Firstly, thank you for allowing me to present here. And this is given on behalf of the group at Royal Holloway, who've contributed to a lot of this, and this represents a lot of our work together. So bridging the machine detector interface. So in the machine detector interface, we typically consider or try to isolate the experiment from the machine, and the machine is something to deliver a beam or in a collider to a particular point, and then the experiment is situated around that. And a lot of high energy experiments are focused on high transverse momentum interactions and observing them. However, a lot goes in and out in both directions, despite best efforts. So incoming to an experiment, you can have products from residual gas interaction, so inelastic or elastic interaction, leakage from the collimator system perhaps, and secondaries perhaps from beam loss that may pass through and penetrate in, the rock and come into a detector or experimental area. Complementary to that, we also have lightly scattered primaries. So on the outgoing side, for example, not every particle undergoes an interaction, usually a very small proportion from in a collider. And so these can undergo light scattering and then actually continue for quite some way, but be deviated enough that they may eventually be lost. There's also physics debris, so if there's an inelastic collision or there's secondary particles produced. And there's a potential for forward physics or forward experiments where we're purposefully looking in the forward direction. So the goal here is, can we simulate far-reaching particles in and out of the experiment? So there's dedicated detector models, and there's dedicated accelerator models, but can we bridge that gap, and what can we learn from that? And here you really need a combination of 2 different strategies. So there's a very specialized way of simulating detectors and producing Monte Carlo data from them. And there's also specialized ways of simulating the motion of magnetic fields and the particle tracking throughout the accelerator. So how can we combine those and really bridge this interface? On the topic of accelerator tracking, so we need to understand the motion through many thousands of magnetic elements, hundreds to thousands of magnetic elements. And perhaps it's in a circular collider and may make thousands, millions of repetitions in a simulation to get to understand the outcome that you wish to desire. So for that end, there are many specialized tracking codes that do a variety. They typically specialize in different aspects. These are used to calculate the motion of particles through these fields in a very precise and accurate way, without losing precision or accruing errors. And so in these tracking simulations, these are quite specialized for the single particle dynamics. And a common way is then to use these for beam losses, and is to simply evaluate when the particle coordinates are greater than the mathematical definition of an aperture. Here you can see a little cut through of part of the LHC, and we have a definition of the the aperture around the beam envelope. And so when some single particle exceeds that aperture, how it's therefore counted as lost. Of course, this doesn't, in real life, this doesn't, particles don't just stop. On the other hand, a 3D radiation detector model is quite complex and really highly specialized. So it's really bridging these. How do we do that? These detector models are specific to one detector. They're built up over and highly detailed, built up over a long time with many people. So how can we do this in such a way where we can learn what we need to, but without that degree of specialism? So a solution that we've gone for is to use accelerating in JANT4. So JANT4 is a widely used open source C++ library for modeling detectors. So it includes a 3D geometry description, a library of particles and particle physics processes. And so the concept here is to add accelerator tracking to this. So benefit from JANT4, which is regularly developed and updated based on all the latest experiments, and then add accelerator tracking to that. We can benefit a little bit if we build a JANT4 model. Accelerators are typically repetitive or have similar shaped components for a given accelerator. So we can benefit a little bit from that. So the idea here is to use a library of very generic but scalable and proportional magnets that we can build up a JANT4 model in a very quick amount of time, but then include accelerator tracking and benefit from both. There is a subtlety here, and that so a radiation transport model will use Cartesian coordinates. There's no preferred direction, and it has to it would be in 3 dimensions. However, for accelerator tracking, we typically use a curvilinear coordinate system. So the description of the particle motion is with respect to a reference orbit or the axis of the machine. And so the coordinates are, or the changing coordinates is relative to that particular path. Now this allows us to maintain a lot of precision, a much higher degree of precision, but we really have to merge these two if we're going to make a model. And the way we do this is actually not just to build a 3D model of an accelerator, but also to build what's called a parallel world geometry, which is another set of geometry in the with the same world or dimensions, but with a different volumes in it. And here we build a series of cylinders that follow the beamline. Now we can use these and query any point in the 3D model and then query it in the parallel world. And then we can get the coordinate transform into the frame of each of these cylinders, which gives us our curvilinear frame. And that allows us to go between the two systems. So to use the accelerator tracking, but in a Cartesian model. Another little subtlety is that in accelerator tracking, we typically use what are called thin elements. And these are just elements with no length that just give an instantaneous kick to the beam. And these are used for the edges of magnets as an integrated effect of the fringe fields or of the magnet, where the magnetic field is no longer completely uniform, and also for any imperfections. So we can use a perfect dipole for the body, but then insert thin elements which have higher order multipoles to account for any imperfections. So here we actually can achieve the same thing in a 3D model, but just putting a very, very thin volume in place that will give the same results. So this is this solution, as it were, actually was thought about and started by Graham Blair in 2004 at Royal Holloway and our simulation group there. And it was originally for linear collider backgrounds. So it's all wrapped up in an application called Beam Delivery Simulation, or BDSIM. And the idea is, as I've described, to make automatic models of JANT4 models of accelerators. It's now quite mature. It's been redeveloped and actively developed since around 2013. And our group's applying it to many different machines. So for ILC or click, for example, for muon backgrounds, where you have secondary production, such as muons, transport through the beam pipe, and then interaction with matter, perhaps in the yoke fields of magnets, and then back into the beam pipe and perhaps through rock, but still reaching the detector. Awake for their final dipole, there was an old colleague who worked on that. XFEL for undulator dose, LHC collimation as myself, and also, which I'll describe later, for Atlas non-collision backgrounds and phaser, which is a forward search. And recently, one of our colleagues, Will Shields, has been working towards medical applications. So although we started with high energy applications, is to really take it down to low energy, where such medical beamlines require the interaction with material and degraders, and also beam forming and shaping. And here's just a little bit of validation. So this is a single pass beamline with a highly varied set of optics, ATF2 in Japan. There was a practice for the linear collider where we validated the machine and the optics, and there's a publication describing the implementation here. One thing is that is integration in data. So, you know, it's great. We have a Jant4 simulation, or we have one that can deal with accelerator tracking as well. But how do we make use of that? What information do we take from it? How do we understand what information we get? There's so much you can take from it. So a few practicalities are that we have a modern build system. We use, of course, Jant4, root, and CLHEP. Our data is written out to root format, and this is something that's widely used in HEP. And the structure is a per event structure. So this allows us to filter and do selections, and a very typical HEP analysis that people would be familiar with in a detector community. As you can see, a little screenshot to the right here, as well as a bit of trajectory storage and filtering. So, if I have muons at a particular plane, where did they come from? Or they came from something that impacted here, but was scattered earlier on here. And understanding these histories is really, the data format and the analysis is really key to this. Here is just a little screenshot. So we also put in yet another parallel world, is invisible little planes, which can record the distribution of particles. And we use these for validating the accelerator tracking, also to understand and record data interface planes where we might hand off to another dedicated experiment. So using this, we have made a complete model of the LHC. So I'm only showing just a small bit here. It's actually very hard to visualize because it's quite narrow with such a big shape. We have optical validation, so we match the beam transport throughout. We have some specialized geometry, but still we go to a level of genericism in that. And we're validating it for proton and in fact ion collimation. So here particles lightly impact a collimator. This is a left to right is the machine in a linear sense that follows it with eight straight sections in 8 arcs. Here, this is IR7, where a lot of the collimation is. And a zoom in here shows you, so in the top is the beam loss monitors, the radiation monitors strapped to the side of the machine. Our simulation of energy deposition in all of the magnets, and then a more conventional tracking simulation that includes some physics in the collimators and some secondary proton tracking. And so really the top one is what we measure, and then we have to go from understanding really to the measurement and between. Application of this. So one of our students, now postdoc, Stuart Walker, he made a much more detailed model of 500, well, about 300 to 500 meters leading up to Atlas in one of the interaction points, so including all the geometry of the tunnel complex. And you can't really see, it's quite small here, but there is a beamline of all the magnets throughout, as well as some of the geometry you can see here for the specialized shielding blocks. And so the purpose here was to simulate beam losses and leakage from the collimator system, and then propagate it through with all the interaction of material up into an interface plane before the detector, where we could then hand off to a dedicated Atlas detector simulation, and then understand hits in the pixel detector coming from non-collision backgrounds. And on the right here, you can see a spectra of what was simulated up to the interface plane. And then also in the bottom is the origin of, for example, for muons that reach that interface plane, their angular distribution and their original creation point to understand where they've come from. Using the same model, another one of our PhD students, so Helena Lefebvre, you can actually, if you go to this link, she's got a poster today and a really quick couple of slide presentation. So using the same model, but developing it further with more detail and actually using it backwards. So this time looking at things going out from the IP is for phaser, which is a forward experiment from Atlas that would be put in a small side tunnel, looking through the wall, as it were, back towards the Atlas IP. So here we're propagating head-on collisions through the complete accelerator lattice and also surrounding material to predict the muon and neutrino flux observed by the detector through the tunnel. And so I would really recommend having a look at that. It's quite an interesting topic. Another topic that sort of leads on from this is physics debris. So obviously, as I said, people typically, the detectors are designed to detect things with high transverse momentum, but also it's quite interesting. There is a lot goes forward now. Perhaps this is maybe not, I mean, it's not surprising and not so interesting, but there are a few interesting facts about it. I'd quite like to simulate this and understand it. So we can have elastically or inelastically scattered but intact protons that come from the collisions. And we can also have secondaries from inelastic collisions. And here's an example spectra. And so what we find is, and this example is in LHC, and part of my work with the collimation group here, we find that at certain points around the ring, there are radiation monitors which are highly correlated with luminosity and not the stored intensity, so not the amount of beam that's in the machine. And these, well, again, maybe not surprising, but what is surprising is these that can often be very far from the experiment, and you can actually even halfway around the ring or all the way around the ring. It's more of a curiosity. It's not a problem for the machine. The beam loss monitor system is used as a protection mechanism to avoid any quenching of the superconducting magnets. But it was more of a curiosity, and also we wanted to understand it so that it wouldn't be a problem for high luminosity LHC. But I want to understand this more, and we have this ability to make a detector model, in effect, of the whole accelerator. So this is what I've started simulating. So simulating head-on proton-proton collisions. I'm using CRMC as an event generator with the Sybil model. And I'm propagating particles in both directions from IP1, IP5, and IP8. Now, IP1 and 5 are the two called the two high luminosity interaction points for Atlas and CMS. And then the other one is for LHCb, which has a lower luminosity and a lower crossing angle and different magnetic optics. So what you see here is a combination of all those simulations. So I'm simulating head-on collisions, each IP, propagating them, and then I'm doing that for each IP, and then doing a weighted combination according to the luminosity. And so what you see here, this is the energy deposition in each component in the model, and then scaled according to the luminosity in the cross-section. So this is the power, as it were, of energy deposition we expect during the running machine. And what you can see is that although there's a lot situated around the particular IPs, there are actually losses throughout the machine which come from the physics debris. Now, you might say that, well, they're sort of linearly distanced from the particular one, but this is looking in the middle of the machine. You can see some are from the closest IP, but some are also even interleaved from other IPs on the other side of the machine. So we can have things that can reach really quite far and be related to particular experiments. So the idea here is, can we make use of that?
You have 2 more minutes.
Okay, thanks. This isn't, however, what you would actually see in the real machine. If you looked at the beam loss monitors, this is the energy deposition in the magnets in the simulation, and then outside of them would be beam loss monitors. So we would, to really make the proper detector model, we've modeled an individual beam loss monitor here. This is made in a Python package also developed for geometry preparation and conversion. And then here's a calibration model where we run a very detailed, down to very low energy model of the gas interaction to get a parameterized model, which we can use in a much more efficient way in the bigger model without having such low energy cuts and interactions. And so the goal here is really to place all of these in the model and to understand the physics debris fully. One thing that we've noticed is that for really long-term tracking, so not just single turn, but maybe thousands of turns, we don't conserve, it's like not conserving energy, but it's really the phase space of the emittance would seem to blow up. Now this is called symplecticity, or a lack of symplecticity. And here it's not because of the algorithms used, which are designed they're designed to be symplectic, but actually that there's a convergence on the intersection with volume boundaries, and there's little gaps between all the volumes, and this really builds up over time. And so our goal is really to eliminate this with a much more integrated approach to tracking. And there are several ways we could do this. One is to use a tracker and then pass to the 3D model when the time is right, but that's a bit specific. Another one is to have only a 3D model when you have a region of interest, maybe a collimator or a target, and then deal with a tracker in between. However, there's no possibility for physics here. And so what we're working on just now is actually really integrating and overriding the tracking in JANT4 to maintain both the Cartesian and the curvilinear coordinates. And a consequence of this will also be a vast performance increase, which is necessary when we have to run millions of events for the required precision. So just to conclude, it's a bit of an introduction on how we might go about this. So it's how to bridge the machine detector interface, how to simulate these two things by creating such a model and the accelerator tracking, and tracking all particles in an accelerator. So hopefully I've illuminated a little bit about how you would go about that. And just as conclusions, we have a full model of the whole LHC in JANT4, and we're understanding the physics debris from that, and in the future will be fully symplectic. And yeah, if you have any questions or anyone's, yeah, thank you very much.
Thank you very much for the very interesting and colorful presentation.
Yeah.
So the session is open for questions. I may start with one. You mentioned the awake experiment. We had a nice presentation today.
Yes.
In terms of a plasma wave field acceleration, typically we use particle in cell codes. So is there any intention to build another bridge, actually two bridges, because it should be one to the Monte Carlo simulation, one to the accelerator part. Did you think about this?
Yes. So for Awake specifically, what we did is it was actually not used for the plasma interaction, but it was used for the calibration of the dipole and the understanding of the screen at the end. But yes, so I guess perhaps the plasma interaction is really quite a complicated one and difficult to bridge with. However, a sort of similar concept is collective effects in accelerators. So this is where particles interact with each other. We've seen for high intensity beamlines, collective effects, space charge are really important to actually get the losses correct. And just now we're doing single particle dynamics where each particle is assumed to be independent, which works well for the things we do. So yes, there's actually work just now on how we can bridge collective effects, how we can do that actually, and whether we do it after each element or we do it as we step along throughout the thing, and to make use of existing libraries, because again, it's quite complicated to simulate. But yes, I think that's something we're looking at. We'd actually started looking at it for medical applications at low energy, where it's also very important, and for electron beam transport as well. So it's we don't have, there's not something immediately just now, but it is something we're working on.
Okay, very good. So good luck. It will be very interesting to see some results in the next conference in 2 years. In person, hopefully.
Yes, hopefully. Thanks.
Any more questions? Audience? Okay, today everybody was very clear, so no more questions. Thank you again, Lori. So next talk and last talk will be given by Haoyu Shi on studies of the beam background at CEPC. Is from ICHEP from Chinese Academy of Science. Please.
Hello, can you hear me?
Yes.
Okay, I'm going to sharing. And can you see my slides now?
Yes, perfect. Please go ahead.
Okay, great. Okay, thank you for introduction and good afternoon. I'm speaking on behalf of the CEPC MDI Beam Background Study Group. And today I'm glad to have a chance to sharing with you the latest study status of CEPC MDI Beam Backgrounds. My talk contains three parts. Oh, sorry. My chart contains three parts: the motivation and some of the study details and the outlook. But to begin with, I'd like to give you a short introduction of the CEPC project itself. As you may know, CEPC stands for Circular Electron and Positron Collider. It is a designing future lepton collider. The CEPC conceptual design report was published in November 2018, that is 2 years ago. And some key CDR parameters and the conceptual figure of the project are shown here. And for now, CEPC is a 100-kilometer double ring design with a crossing angle of 33 milliradians. To achieve the physics goal of CEPC, we will need an excellent accelerator and detector in good performance. And to push the performance best, we will need better to take the focus, which may impact the performance as much as possible, into consideration, even in this early design phase. Among the factors, the background is one of the most critical issues. It may impact the detector in several ways and have to be well studied. Our study flow of the backgrounds contains three aspects: design, simulation, and benchmark. The loop of the study flow means that we must keep evolving together with the whole project itself. The flow starts from and will go back to the design, the first step. We must take one particular design as a baseline of our study. Now we take the original CDR design of both CEP's accelerator and detector as a baseline. Here shows the layout of the downstream part of the CEPC interaction region. For the first step, we will focus on Higgs mode and take only one IP and one beam into consideration because they should be symmetric. And since it's still a preliminary study, we only study the background impacts on vertex detector, which will be the closest detector to the IP. And most part of our study was based on the step two simulation. Before we actually perform the simulation, we must have a general idea of the sources of the other background. For CEPC, we will have three kind of effects: the single beam background, luminosity-related backgrounds, and injection background. But the last one, injection background, is very hard to simulate. So we plan to think about it in the further study, not now. And from the particle type of the primary, they are mainly photons and of energy beam particles, that is electrons or positrons. The simulation workflow contains three steps also: generation, tracking, and detector simulation. We use several generators to generate spectra for selected backgrounds. For some of them, we're using the well-known existing generators, and for the other, we will use our own formula-based generators. We do have some cross-check of these two. Then we put the spectra into the tracking tool to record the loss distribution within the interaction region. Finally, we will use the interaction region loss distribution as a source to perform the full detector simulation. And to quantify the impact on detectors, we will use heat density, GID, and NEO, and adopted the Atlas way to estimate. Our first step is the basic simulation to have an idea of how worse the background will be. We will take several backgrounds using their own generators to get the spectra. And for tracking tool, we are now using SAT and BDSIM. And for detector simulation, we are now using a tool called MOCA based on Gen 4. For photon backgrounds, we only studied synchronous radiation and beam straddling, or I could say pair production. The synchronous radiation, which may impact the interaction region components, were mainly generated when the beam passing the last bending magnet of the final focusing. So we use beta sim to transport the beam particle from the last dipole, and then use Gen4 as the generator of it. Here we show the spectrum and also the impacts of the synchrotron radiation. Pair production means the photon backgrounds from beam straddling. We use GenPig++ as a generator and implementing the detector solenoid and other magnetic field by code updating ourselves. Here shows the TID and NEO spectra of the pair production. And the other important source is off-energy beam particle, contains beam gas, beam straddling, beam thermal photon, beam straddling, and radiative Bach. We choose these four among all the off-energy beam backgrounds because of our short lifetime, several hours or even several minutes. Shorter lifetime means more lost, including in the interaction region, and higher impact on the detectors. Let's dive into them one by one. Beam straddling was generated as the IP, and for the spectrum plotted by our own generator, we can see a very narrow peak. And the tracking here confirms that most of the loss happens after second turns. And compared with beam straddling, the spectrum of the radiative Bach plotted by BB Bram is much wider. The scattering also occurs at the IP, but the lots of them would be immediately get lost. That's a red peak on the downstream part here told us. Beam thermal photon and beam gas beam straddling are different stories. They were not only generated as the IP, but also everywhere in the whole ring. The spectrum of the beam thermal photon plotted by our own generator shows a relatively wider one compared to beam straddling. So it may have some immediately lost here as a right line, and also some multi-turn lost as well. And for now, we only generated the scattering within the interaction region and also the 200 meters upstream of the IP. And the spectrum of the beam gas beam straddling plotted by our own generator 2 also shows a wider spectrum down to the 0 and up to the energy acceptance, which is 1.5% in the design for now. And for beam gas, we assume that the residual gas is carbon oxide and the pressure is 10 to the minus 7 Pascal. But different than others, beam gas beam straddling also has some zero turn lasts, with the green line shows here, means that this particles lost immediately after scattering, even before the reach IP. So combine these four and normalize to the y-axis to the loss rating hertz per 10 centimeter, we can find that beam straddling contributes the most, as this line shows here, and the total loss were also high. The contribution from the upstream loss may be slightly higher than the downstream loss, which is very bad news. So we must do something to mitigate. For our aspect, mitigate also means optimization. And for design, we put some masks and collimators. And for simulation, we are trying to be more accurate. So we are trying to simulate the scattering in the whole ring for beam gas, beam straddling, and beam thermal photon, not only 200 meters. For photon backgrounds, we have synchronous radiation and pair production. So for synchronous radiation, we put 3 masks designed here on the upstream part of the interaction region to shield the SR. And it turns that works. The heat density and also TID were several orders lower. But however, the pair production was very difficult to shield, so we just skipped to the off-energy backgrounds. Now we are used 2 sets of horizontal collimators located around 2,000 meters away from the IP to shield the off-energy beam particles. And for now, we assume that they were ideal ones because they were only checked in the tracking tool. It do not contain the interaction between the collimators and the particles, and then study their effects. We are trying to add more, but it's still under study. And the collimators works also at least on simulation. We can see from the comparison for both for affects that almost all the upstream loss here, here, and here were almost gone, except for the last one beam gas bremsstrahlung, because they were someone here were generated as their return up and get lost before they reach the IP and after the collimator. So we combine these results again, and in this time we do not need to worry about beam strahlung. We also perform the detector simulation using the loss in the interaction region as a source. And we apply a safety factor of 10 and less the impacts in the first layer of our vertex detector. We can see from the chart that it may still higher than the tolerance of the vertex detector now we are designing. And among all the backgrounds, the beam gas bremsstrahlung contributes the most. Therefore, we have to think about further mitigation. We also list all the static status of the simulation here. We may need to optimize what we have done and sort of thinking about what we haven't yet. And the last aspect of the study flow is benchmark. It is important to validate the model as well as the code, both based on literature results and experiments. And for experiments, we are considered to study on BPC2 or BES3. The basic principle of this study is to distinguish the single beam one and luminosity related one. Then the data or Monte Carlo comparison could become possible. And we have did a 2-hour experiment last summer by changing some machine parameters, but actually the results were not well. The results from experiments and the simulations did not match, or even the fitting itself is still struggling. So we plan to do it again with well preparation and maybe a longer time. And it's time to summarize. From the simple checklist here, we can learn the goal and the status of our study. And in the future, we are sure to optimize our study both on design, simulation, and benchmark. And we may take some new baseline and put our machine mode like Z and W and other detectors beyond the vertex detector into consideration. And that's all of my talk today. Thank you for your attention.
Thank you very much for the very clear talk. So we have a lot of time for questions. Anybody? Yes. Massimo Caccia, please.
Hello, this is Massimo Caccia from Università dell'Insubria and INFM Milano. I have a question. If I got it right, when you sum up the contribution, you get to something of the order of 11 hits per centimeter square per beam crossing at the innermost layer of the vertex detector. Now, this is telling me the average, but do you have any indication about the azimuthal distribution of the hits? They are all equally spread over 2 pi, that I guess not, or they have anisotropies?
If I make your question clear, maybe not. For now, we only study the electron and electromagnetic showers. Can I get your question right?
Yes, can you maybe go to the summary slide where you have the different contribution at the innermost layer of the vertex detector?
You mean this chart?
I mean here, yes. So yeah. If I look back, heat density per centimeter square per beam crossing, and I got up to 12, let's say, which is fine. But these 12s are actually distributed evenly, uniformly over pi or over phi, or you have a concentration in specific regions of phi?
This is, we took the highest number, not integrated over phi or any. We just took the highest number and then.
But since you generated the heat, you're supposed to know whether in azimuth, in phi, they are evenly distributed or not.
They are not evenly distributed.
Yes, this is what I was guessing. And the density is higher on the horizontal plane.
Yeah.
Okay.
Okay. Any more question? Okay, if not, let's thank the speaker again. And I would like to thank all the speakers for the very high quality presentation today. This is the last block of session 11, Accelerator, but I would like to remind you that there will be a poster session today at 1:30 p.m. Central European time. So please, if you are interested, you can take part in the poster session. And yeah, thank again and enjoy the rest of the conference.
Thank you. Bye.
Thank you. Bye.